Hello, everyone. As the general co-chairs, Sara and I welcome you to EAI International Conference on Security and Privacy in Communication Network, aka EAI SecureComm 2020. This is the 16th conference built upon the successful conferences in the past 15 years. This year, it was originally planned to be held in Washington, D.C., United States, but due to COVID-19, it became a fully online conference. None of this would have happened without the effort of the organizers behind the scene. We had an excellent team that had worked very hard to organize SecureComm 2020. First, we would like to thank TPC co-chairs Kevin Butler and Nitesh Saxena for leading the paper review tasks. We are very grateful to other chairs of the organizing committees, including Conference Manager Alexander, Publication Chair Noson Park, Workshop Chair Chi Li, Local Chair Hemant Purohit, Poster co-chairs Dave Tian, and Malihi Shamania, Publicity and Social Media co-chairs Emanuela Marasco and Carol Fang, and Web Chair Peng Binfeng. We also thank our steering committee chaired by Bruno Kessler and Guofei Gu for their continuous guidance and direction, and also our patrons for their warm support. We must thank the program committee members along with external reviewers for them a great job in paper review. We also thank the authors who submit papers to SecureComm 2020. Finally, we thank all conference participants for making SecureComm a success and hope that you have an enjoyable and fruitful experience by attending SecureComm 2020. Thank you.
Hi everyone, this is Nitesh Saxena, one of the TPC co-chairs at SecureComm 2020. I, along with my colleague and co-chair Kevin Butler, welcome you to the program. So SecureComm, as you know, is one of the premier venues for discussing research in secure communications and networking. It's a very focused conference, quite visible in the space. And this has been going on for several years. This is the 16th year we are organizing the conference. And clearly this is the first time we are holding the conference in the remote mode thanks to COVID-19. So as chairs, we would like to thank the steering committee for giving us the opportunity to lead the conference. It's been a great experience working with the team at EAI, the general chairs, and the PC members. And I think everyone has worked really hard to put together a program that we hope all the audience will like. So in terms of the technical program, the organization was mostly done by the TPC chairs, but I think the general chairs also had a leading role in the logistics of the organization. And then most of the work alongside the reviews was done by the TPC members. So we had recruited 66 members from the pool of our community, and they are all great researchers in the security and privacy area, generally defined. And we try to balance TPC in terms of the areas of expertise. And as you know that the reviews were done at the time COVID-19 was at the peak, but we still managed to basically cope up with our advertised deadlines. And I really appreciate the work done by the PC members in turning in the reviews on time and involved in a lot of discussions on the papers. So just a quick sort of snapshot of the program. We received a total of 120 papers, out of which we selected 40 full papers and 7 short papers. We also have 10 posters, which were also actually reviewed and selected to be presented in the program. Each paper received, I think, on an average, 3 reviews. Some of the papers probably had a little less, maybe 2 reviews, but most of them had 3. And we had a healthy discussion among the program committee on each of the papers, and we selected these 40 full and 7 short papers. Some of the good papers could actually not be presented in the program. They were still high quality, but we had to reject them due to the lack of space. The program has been organized into 10 based on the category of topics they belong to, and they are broadly, again, the topics in security, secure communications, and networking. The poster session, again, has 10 posters, and we also have a workshop called Emergency Comm. It only has few papers, but I think these are high quality papers. So yeah, so that's basically what I wanted to kind of say in my opening remarks. I hope that you will relax and sit back, enjoy the program. And now I will hand it over to my colleague, Kevin Butler, who would add some words of wisdom. Thank you.
Okay, thank you, Nitesh, and welcome again to attendees. I'm Kevin Butler. I'm the co-chair of SecureComm this year, and I just wanted to say a couple of things about the program committee. So Nitesh has talked about the structure of the program and the people who made this all happen. I just wanted to say a little bit more about the program committee. So we had a total of, there were 66 PC members, 64 forming the PC, and then the 2 of us as chairs. This was a multinational effort with over 4 continents represented by the TPC. So we were very fortunate to have a lot of people joining the PC from all over the world, providing their own perspectives, experts in a number of various areas, from cryptocurrencies and blockchain to physical layer to networks and mobile devices. So a really wide range of expertise, and we're very thankful for that. There were over 660 recorded comments in HotCRP, our conference management software, and over 250 reviews were recorded by the TPC members. So there's a lot of effort that was put in a relatively short amount of time for covering both the regular and late-breaking paper tracks. And we're very thankful to our PC, and we wanted to take a moment now to acknowledge the members of the program committee. Nitesh and I are extremely grateful for your efforts, and we're happy with the tremendous program that you've put together. These are all of the folks. If you happen to see them online or in a chat session, please do make a point of thanking them for their efforts. They really did do a lot of work to make this conference a success. And with that, we're ready to move to our first technical session. So please enjoy the rest of the conference, and I look forward to seeing you in the chat session and online in this virtual event.
Dear ladies and gentlemen, my name is Karolina Martinova, and I would like to welcome you to the EAI SecureComm 2020. Unfortunately, due to the virus, I am not able to meet all of you in person, so I'm using this opportunity to address the organizing committee, the authors, and the participants on behalf of EAI. This way, I would like to thank Dr. Kunsun and Professor Sara Foresti in particular for their work as general chairs. I would also like to recognize the significance of a thorough peer review of this conference, which was organized by the program committee chairs, Dr. Kevin Butler and Professor Nitesh Saxena. The whole organizing committee has put in hard and excellent work, which deserves gratitude. Today, during this streaming, you can actively participate in 2 ways. Firstly, you can join the Q&A on Slack through a link that you can see below this video. Upon accessing the EAI SecureComm 2020 Slack workspace, you can enter all the channels which are divided by sessions. Secondly, you can vote on individual presentations and leave your fellow presenters' feedback on their work through EAI Compass. We will shortly show you how to access this platform and how to leave and receive feedback for presentations in this conference. I would also like to use this message to invite you to join us again at the next year of SecureComm conference. EAI SecureComm 2021 will take place in Kent, United Kingdom in September. Should you be interested in becoming a part of the next year's organizing committee or technical program committee, please do not hesitate to contact me at my email address below. Similarly, if you're interested in discussing other possible cooperation, a conference, a workshop, or a new event altogether, please contact me at my email address as well. Now, my colleague Michal will present you with what EAI does, who we are, and how you can get involved in our various activities. Thank you for your attention.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Okay, this is joint work between myself and Stephen Farrell, a colleague at Trinity College Dublin, and it's looking at the privacy of the Singapore COVID contact tracing app. So this work was done back in April, which seems a long time ago now. It's a fast-moving area, but I still think it's quite relevant actually. And I'll try and make clear why I'm saying that. And so in the talk, I'll be talking about things that are a little bit more recent than the original Singapore app and try and put things in the current context. Okay, so the Singapore app was probably the first one, to my knowledge, that used Bluetooth for contact tracing. And so it started many things off. But since then, there have been many more apps. In particular, there's many apps based around the Google Apple API, especially in Europe and increasingly in America. But all of them use the same idea. They use Bluetooth to measure, to infer contact events. And the basic idea is that one device transmits Bluetooth beacons, another device receives them and records the signal strength that the beacon's received with. And the hope is that if signal strength falls with distance, then by thresholding on signal strength, we can get a rough idea of proximity. And so this graph on the right here these are actually measurements taken using two handsets outdoors in an open space, and we can see that the received signal strength decreases with distance, although it's somewhat noisy. And it decreases by around over 2 meters, which is an important number. We'll come back to it. Decreases by around 10 dBs. I'll come back to that number in a minute. Now that's clean conditions outdoors, but of course these devices are used indoors a lot and in more complicated environments, and that can change things a lot. So in our measurements beyond this current talk, but just to put things in context, things we found that can have a big effect on the Bluetooth received signal strength are differences between handset models, how the antennas are packaged inside and what chipsets are used inside the handsets. The relative orientation between handsets really matters. Small changes in rotating face up, face down can make a big difference to the received signal strength, with everything else otherwise held constant. This is the Bluetooth transmits the 2.4 gigahertz band, and so there's problems with absorption by the human body, if it's in your pocket or if it's in a handbag. There's, of course, indoors and enclosed spaces, reflections from walls and floors and ceilings and furniture, and that's a particular issue in areas where there's a lot of metal, so in trams and buses and trains, public transport, where the walls, floor and ceiling are all metal and a lot of the furniture is metal, and so there's many reflections. And also in places like supermarkets where the aisles are often, shelves are often made of metal. And so measurements separately from this can easily show plus minus 10 dB variations, both increasing and decreasing signal strength due to those kind of effects. And so that's comparable with the change over the 2 meter distance, and that's the source of a lot of the ongoing debate about the efficacy of these apps. But putting that to one side, this isn't a talk about efficacy, it's about privacy. The Singapore app, as I said, was the first one, to our knowledge, that was widely deployed using Bluetooth. OpenTrace is an open source release of Trace Together. There were several versions of Trace Together released. We're going to look at primarily the OpenTrace one. And of course, subsequently, Apple and Google have released their API, and many apps use that. But actually, it doesn't change the basic idea behind use of Bluetooth, and nor do some of the privacy issues change either, as we'll see. Okay, so what are the privacy concerns? One is that these are normal apps. So first of all, there's a lot of public interest in the privacy of them, which is unusual in itself. But also, these are government-sponsored apps, so the health authorities in countries typically are heavily promoting the apps to their general population, saying everyone should install these for the benefit of their population. And so it's not very often common that the government says you should install this app. And so that changes the context for the apps. And so the discussion to date around privacy is often focused on architectural issues, decentralized versus decentralized and so on. But in this work, we take a look at the actual app implementation as deployed and look at what data is sent. And the reason for that is that there could be bugs or poor software choices or unexpected dependencies, and leading to data being sent that wasn't expected, even regardless of whether it's centralized or decentralized. And the main privacy threats are, of course, the data sent in messages between the apps and backend servers, but also the metadata. So every time an app a device connects to a server, then of course it reveals its IP address. The IP address is a rough proxy for location. There's very standard services for mapping from IP addresses to location. And so if those messages can be linked together, multiple messages from the same device over time can be linked together. That gives a location history over time, and there's lots of examples of that the time histories are relatively easy to de-anonymize. And the rough idea is that, if you know where you are during the day, you know where you work. If you know where you are during the evening, you know where you live, and you don't need too much more information to de-anonymize. So there's interest in whether these messages contain identifiers that can be used to link them together from the same device. So what did we do? We downloaded OpenTrace. We followed, it's actually nice, everything was straightforward to set up the back-end services that the app talks to, compiled the app itself and installed it on a rooted phone. The back-end traffic between the phone and the servers is encrypted, of course, and so we need to do some work to break the encryption and carry out a man-in-the-middle attack. So we used Frida to decompile the code, used Frida to figure out where the checks were for certificates, overrode them, and that let us see the traffic. And up in the top right there is an example of the sort of traces that we see being sent. So that was the bulk of the technical work in this project. So what did we find? So the first thing we found was that OpenTrace uses Firebase for its backend, Google Firebase, and so immediately there's two parties handling data. So there's Google and there's the health authority. The first thing within Firebase that's used is Google Analytics, also called Firebase Analytics, that's used to track user events. So for example, when the app's opened, when it's closed, and because of that, that creates a steady stream of messages to the backend servers. And here's a little picture of the sort of information that's made available that would be in the Google dashboard to the health authority. And I will zoom in a little bit on that. And we can see that the sort of information that's available. So this number up top here is an identifier for a user. It's a Firebase ID. We can see the kind of telemetry, so the start when the app became active, different screens viewed, and a series of events with timestamps, dates and timestamps. We also see the rough location and so on, and the amount of time the user was looking at the app. So there's quite a lot of analytics immediately being made available to the health authority. And of course, there's more fine-grained stuff. The IP address is concealed here, but Google can see the IP address. So even if they're masking it from the health authority, they're not masking it from themselves. So use of analytics in a privacy-sensitive app like this that the governments are proposing for population-wide deployment seems problematic to us. The second part of Firebase that's used by the OpenTrace app is the Firebase Functions, and that's used to provide the server functionality in the cloud. And it's very convenient, of course, but it's also not so private. So that's used for storing data, for delivering information to the app. And Firebase keeps on the servers a detailed log of every function call per user. It's used in the phone also uses Firebase Authentication, which is to store phone numbers. So the Singapore app requires a user to enter their phone number. They receive a PIN code. They have to re-enter that to verify that it's the right number, and then they can proceed to use the app. So it's linked to phone numbers in this particular app, and those phone numbers are stored using Firebase Authentication also. So that's personal information of the Singapore population or whoever else is using this app, because very similar apps are used elsewhere. And may or may not be an issue, but Firebase Authentication is always run on US servers. So Google has many servers around the world, and sometimes things are hosted locally, but the authentication service is always run on US servers. And that's probably fine if you're using an app in the US, but if you're using it in Singapore or another country, you might be more concerned about that. So here's the kind of dashboard that you'd see from the back end of Firebase functions. Again, this is for a particular device. This is the log. You can see that it logs the UID, so it's got the particular device information, and each individual function call, when it happened, is recorded. So there's quite fine-grained information about the communication from the app into the service here, broken down by individual devices. And so what data is actually sent? So this is an example of analytics packet sent to appmeasurement.com. That's a Google domain. And there's binary stuff in here we could decode, and we'll actually see that telemetry data. But just having a look at the raw binary data, some strings jump out. One is this first string here is the Google advertising ID for the phone. This second one is an app instance ID, which is linked to the particular copy of the app that's running on your phone. And this is a Firebase ID, which is used for available on those dashboard. Those two quantities are seen on the dashboard. And the Google advertising identifier is linked to your phone. It's manually resettable by the user. So that means that there's these three long-lived identifiers that link together all of the communication with the Google servers. So, and more recent work, actually not discussed in the paper, but I'll mention it here. Is OpenTrace requires Google Play services to be enabled, or it doesn't work. So the use of Firebase is a component inside Google Play services. So it has to have Google Play services enabled, or else it just doesn't work. It will stop at the point of entering the phone number because it can't contact the Firebase functions. So we also took measurements where we minimally configure a phone so we switch every setting we can find to do with the Google Play services off. It's just enabled. There's no Google software, no Google apps enabled, and every setting we can find was switched off. And so about Google Play services itself, when it's just by being enabled, generates a bunch of connections, and these are separate from the Firebase connections generated by the app. So regardless of what the app is doing, how it's using Firebase, the very fact of enabling Google Play services generates all these connections, and we observed connections roughly every 20 minutes to Google. And there's several sorts of connections, but there's two that I'll just highlight. One is that roughly 4 times per day, not per data, it makes a call to check-in endpoint, and that is packed full of identifiers. So this is an example of a call. It includes the phone number. That's down at there's the phone number there. It includes the email that the phone is registered to. It includes the hardware serial number. That's this guy here. It includes the IMEA, which is a network, which is the hardware number. It includes the serial number just mentioned, the SIM serial number, the Android ID, which is a persistent identifier on the phone that can only be reset by a factory reset of the phone, which of course clears all the data. Wi-Fi MAC addresses on there. There's this NID cookie up here, which is used to link lots of calls back to Google servers, and it's got this other thing here, which is another kind of cookie. So it's packed full of identifiers. This particular one that's sent just by enabling Google Play services. And then more frequently, there's these log batch calls, which are recording. They're sent quite frequently, less than once an hour or more frequent than that even. Sharing information on the handset, so running processes, the errors, telephony information. And these are all linked together with this NID cookie. So it's saying quite a lot about the life of the phone is being sent back to Google just by enabling it. And so, of course, that's a concern for these privacy-sensitive apps. And so, in summary, we would say to people using the OpenTrace and using these apps more generally. Don't use Google Analytics or Analytics generally, or at the very least allow people to opt out of them. Don't use Firebase and remove the dependency on Google Play services, because the very fact of forcing people to enable Google Play services immediately makes it hugely intrusive. And not really commented on this topic. There's some crypto issues in the way the personal information is encrypted inside the OpenTrace setup that we've got recommendations for improving. Thank you.
Welcome to my presentation. I am Hao Huang Wen, a PhD student from The Ohio State University. Today, I'm going to present our study of the privacy of the COVID-19 contact tracing apps. This is a joint work with my colleague Qingchuan Zhao, my advisor Dr. Zhiqiang Lin, as well as Professor Dong Shan and Professor Ned Schroff at OSU. The COVID-19 pandemic has spread across the globe and caused tens of thousands of loss of lives. To fight against this pandemic, contact tracing is widely recognized to prevent the spread of the disease. Essentially, contact tracing is to identify people who may have come into contact with an infected person. And there are many techniques to achieve this. In early years, manual interviews were used to keep track of an infected user, which was not so effective. As a result, there are other digital contact tracing techniques, such as camera footage, credit card transactions, and cellular network. So far, contact tracing app in smartphone is considered one of the most promising solutions, since smartphones are ubiquitous and have many sensors and communication channels. Today, nearly 50 countries have released their official contact tracing apps. However, many of them lack transparency, and thus have escalated concerns regarding user privacy and security. In the past few months, it was reported that many of the contact tracing apps raise privacy concerns, including data leakage and de-anonymizing users. There have been a number of works in analyzing contact tracing applications. For example, some open source protocols are analyzed, such as DP3T, MPC, and the exposure notification from Google and Apple. There are also works on analyzing contact tracing mobile apps, such as those released by the Singapore and the UK. Meanwhile, many contact tracing apps on the Android platform have been studied as well. To advance the state-of-the-art, our goal is to perform a systematic and cross-platform study of the contact tracing mobile apps. Before presenting our study, I would like to provide some background knowledge about contact tracing apps. With respect to the contact tracing techniques, they can be categorized into two types. The first type is location tracing, in which the exact locations of a person has visited will be collected. And these locations will be linked together according to the timestamps. There are two types of such data. One is continuous coordinate-based GPS data, and the other is discrete places-based data, such as those collected using QR code checking. The second type is proximity tracing, in which the app only estimates the distance between users without knowing the exact location. In proximity tracing, the Bluetooth Low Energy, short as BLE, is widely used. Regarding where the risk is calculated, there are two types of architecture of a contact tracing system. The first type is centralized, where the server calculates the risk and directly informs the high-risk users. The second type is decentralized, and the server only pushes the information of the infected user. Then, the end user receiving the information will perform self-diagnosis locally. Next, I will use a diagram to illustrate the workflow of a contact tracing app. At first, the app generates the contact tracing information for the user, such as user identifiers that can uniquely identify a person. Second, in proximity tracing such as BLE, the app exchanges information with encountered nearby users. In particular, the app broadcasts the identifier through BLE, which allows other users nearby to pick them up. Third, the exchanged contact information will be stored in the local database. Note that for location tracing, the app also needs to record the precise location of the user. Next, if the user is tested positive for COVID-19, all the contact tracing information and location information in the local database will be uploaded to a remote server. Then, in a centralized architecture, the cloud will calculate the risk for all users based on the uploaded information. It will inform the high-risk users based on the calculated scores. However, in a decentralized architecture, the cloud only pushes the infected user information to all end users, so that the end users can perform self-diagnosis locally. Next, I will describe our methodology, and I will start with the analysis of our scope. Given there are many privacy issues, we particularly focus on the misuse of the data being collected for the contact tracing purpose. For example, what type of user data is collected, and can such data reveal the user's identity? With respect to the program code, since we target Android and iOS applications, the program code of our interest is the disassembled or decompiled Java bytecode, Objective-C code, or Swift code. In the following, I will illustrate each step of our analysis in detail. The first step is contact tracing relevance API recognition. Taking an Android or iOS application as inputs, we need to recognize their types. Correspondingly, there are system-level APIs that allow us to identify them, including the BLE or GPS APIs. And we scan if the app contains certain API in the category. If any API in these categories is invoked, it implies that very likely the app has used BLE or GPS for contact tracing correspondingly. The second step is privacy information identification, in which we identify the privacy information collected for the contact tracing purpose. According to the techniques adopted, there are two types of APIs. If the app uses proximity tracing, we in particular focus on the BLE APIs. Specifically, there are two ways for a BLE device to exchange data with another device. One is through broadcasting, and the other is through reading property data on an established BLE connection. As a result, for broadcasting, we focus on the configuration and the advertised data, such as UUID and manufacturer ID. For the property data, we focus on the values being set in the BLE service and characteristics. And we also manually infer their semantics based on the program level clues. As for location tracing, since the location information will be eventually stored locally and uploaded to the remote server, we target the APIs that write the database. For example, there are APIs that execute an SQL statement. Finally, given the privacy information we get, we compare the results across different platforms to check if there is discrepancy between iOS and Android. Next, I will present the evaluation results. In June 2020, we collected 41 contact tracing apps that are released by the government or health authorities, which are both from Android and iOS platforms. In this figure, we show their distribution across the globe. For these 41 apps, we further analyze their official documentations. We find one of them is only available in Android, while the rest, they are available on both platforms. On the techniques perspective, 20 of them use BLE for proximity tracing, 14 use location tracing, and the rest 8 of them use both to improve the accuracy. Regarding the architecture, we can identify such information from 18 apps. Among them, centralized architecture is more common since there are 12 such apps. We find 6 apps use decentralized architecture. From their documentation, over half of them have claims that their implementations are privacy preserving, such as they have minimized the data collection, limited the data usage, and also perform data destruction. Next, I will describe our results and the key findings. For the app that use proximity tracing, we analyze their BLE-specific data. This table shows the results of the broadcast data. Our key finding is that 10 apps broadcast static UUIDs that enable app fingerprinting attacks. This attack has been reviewed in the previous research. With these static UUIDs, attackers can know which contact tracing app a nearby user is using. In contrast, 6 apps use dynamic UUIDs that rotate periodically, which indicates that their developers may have been aware of this issue. We also find one app that broadcasts default device names, which can potentially serve as a unique identifier to track an individual. We have another table showing the results of the BLE property data, as well as the data semantics. Our key finding is that 2 apps store fixed user identifier in their readable characteristics, which allows tracking of a specific user. For instance, if the fixed user identifier appears again in the same location or different locations, an attacker is then able to link these locations and IDs for a specific person. This finding has been disclosed to the app developers. We also discovered that many apps have collected other device information in the BLE property data, such as system version and RSSI, which is possibly for calculating the physical distance between 2 smartphones. As for the apps using location tracing, we present the data collected for these apps. Our key finding is that contact tracing apps often collect device information, including system version, smartphone model, orientation, UI information, and build version, which is possibly for increasing the estimation precision. While comparing our results between iOS and Android, we discovered two cases of discrepancies. The first app is from India, and its iOS version collects device OS information, while the Android version does not. The other app is from Czech, and its iOS version integrates a unique ID in a characteristic, while its Android version does not. We suspect this is due to the different development processes between the two platforms. Our work still has some limitations. First, our set of contact tracing app is not complete, since we failed to download some iOS apps due to the download restrictions. Also, given the fact that the COVID-19 pandemic continues to spread across the globe, many of the countries will also likely to roll out new contact tracing app for mitigation. Therefore, it is also important to vet these newly emerged apps to ensure the user privacy. In addition, there are other research questions such as how secure and efficient are these apps. In order to preserve user privacy, there are two mitigations. The first is to ensure anonymity. In our study, we find the broadcasting of fixed identifiers can allow user tracking and fingerprinting attacks. As a result, developers should use dynamic identifiers that rotate periodically, as demonstrated in many of the apps. Second, it is also important to improve transparency. Many technical details related to user privacy should be open to the public. In summary, our paper makes the following contributions. Represents the first systematic study of the COVID-19 contact tracing apps, with a focus on user privacy. To this end, we analyzed 41 apps from Android and iOS platforms and compared their behaviors. From our analysis, we discovered security issues, including broadcasting of fixed user identifiers that can lead to user tracking attacks. This is the end of my presentation, and thank you for your attention.
Hi, I'm Syed Akiban Reader, and our work title is LaaCan, a lightweight authentication architecture for vehicle controller area network. This work is supervised by Professor Mohammad Zulkarnain, and we are from Queen's Reliable Software Technology Lab, Queen's University, Canada. This is the agenda of today's presentation. I'll begin by explaining the background and motivation behind this research, then I'll describe the security lackings in CAN protocol. After that, I'll present the classification of CAN security solutions and our proposed framework. Later, I'll share the challenges of designing the solution. I'll try to cover the implementation and validation in brief, and finally, I'll conclude this presentation pointing out the limitation and possible future work. Before the emergence of digital electronics in automotive industry, vehicles were considered as mechanical machines. Components such as engines, brakes, gears were assembled into a car in coherence with the principle of mechanics. The limited accuracy of mechanics led to undetectable failures, and vehicle safety was in threat. To improve the scenario, vehicle manufacturers started installing electronic sensors for driving safety and assistance. Electronic Control Unit (ECU) was introduced to control mechanical components and sensor. With the revelation of ECU, the automotive industry evolved to offer safety, comfort, and assistance. All these features, brought by connectivity of electronic components, offer a safe, comfortable experience to drivers and passengers. However, these features expose the previously isolated vehicle system to cyberspace, which introduces the opportunity of cyber attacks. For example, researchers demonstrated attacks disabling the brakes from 10 miles away. In 2016, the Kin Security Lab in China displayed attacks on a Tesla car in both parking and driving mode. They unlocked the door and manipulated brake. These attacks control vehicle functionalities illegally. ECUs are responsible to control these functionalities, and they communicate via a CAN bus. Therefore, these attacks highly relate to CAN communications, and the security of these communications is a concern. The figure shows in-vehicle CAN network where multiple ECUs are connected. The two most significant purposes of CAN development were to reduce the wiring complexity and cost. At that time, security of communication between vehicular components was not a concern, as the vehicle was a closed system without communication with other devices. A standard CAN mask size is 120 bits. I'm only discussing the fields related to this work only. It has an 11-bit identifier that contains the message type and priority of the message. The 64-bit data field holds the transmitted data, and the 16-bit CRC field contains 15-bit cyclic redundancy check code and 1-bit delimiter. The CRC field used for error detection. CAN is a broadcast-based system. It doesn't have any built-in security features. Any node connected to the network can read or send data. The data is unencrypted, so attackers can reverse engineer the network traffic to exploit data privacy. Some of the existing work struggle to ensure strong security, which means that at least one attribute is missing from confidentiality, integrity, and authenticity. The solutions that ensure these attributes have high communication delay. Since the vehicle is safety critical, an acceptable security solution should provide strong security with low communication overhead. In order to achieve this, we classify the existing CAN security solutions in terms of security enforcement procedures, which gives a broader picture of a related work. We also propose a lightweight security framework that implements an authenticated encryption framework to ensure confidentiality, integrity, and authenticity. In order to get a clear overview of existing security solutions found in the literature, we classified the security measures in terms of security features. The figure depicts the classification. With the help of these classifications, researchers and practitioners can select an implementation technique based on their security requirements. The communication is primarily secured by adopting cryptographic architecture or intrusion detection systems. The cryptographic architecture mostly involved different ways of encryption, authentication mechanisms. It is usually implemented in two forms that are distributed and centralized. In the distributed architecture, all the ECUs are responsible for ensuring the security of the network. It means that security features are implemented inside all the ECUs and there is no need for a central authority. The distributed approach is further divided into three categories: encryption, authentication, and encrypted authentication. The encryption approach only encrypts the data. The authentication approach only authenticates, and the authenticated encryption performs both encryption and authentication. As we can guess, the authenticated encryption provides strong security among them as it encrypts and authenticates the data. We found one work that only encrypts the data. Good amount of work have been done for authentication. We have not found a lot of work in authenticated encryption. It can be because of having high processing delay. Authentication is also implemented in the centralized process. Usually dedicated central ECUs authenticates the messages. These approaches may involve some processing in participant ECUs related to authentication code generation, but the authentication is served by the central ECU. It does not provide confidentiality and it is expensive to install dedicated central ECUs. The intrusion detection systems learn the predefined activities and policies to detect and report malicious activity. It can be categorized into behavior-based and knowledge-based techniques. The intrusion detection systems require training of known behaviors and attacks that is heavy for resource-constrained issues. This is why we took cryptographic approach. We selected distributed authenticated encryption as it provides strong security without involving any central issues. Before presenting the proposed approach, I would like to share cryptographic concept authenticated encryption with additional data, or in short AEAD. A network packet usually consists of data and headers. Protecting only the data is not enough as the headers contain crucial information related to data. AEAD algorithms can protect the integrity and authenticity of both plain data and headers. It also ensures the privacy of data by encrypting it. This figure shows the diagram of an AEAD scheme. It requires 4 input: key, norms, plain text, and associated data. It generates a key stream block using the key and norms. The ciphertext and MAC is generated using the key stream block. It maintains an internal counter to keep each operation unique. We propose implementing AEAD for CAN protocol. The figure shows the architecture of our framework. We implement authenticated encryption following the concept of AEAD. Here, we encrypt the data first and then generate MAC on encrypted text. As additional data, we use CAN identifier as it contains crucial information related to message. After the authenticated encryption process, we replace the plain data with the ciphertext and replace the CRC with MAC. As an AEAD algorithm, we select a ChaCha20 Poly 1305. I'll share the reason behind choosing it in the next slide. Now, I would like to discuss 3 major challenges of designing this solution. First of them is selecting the cryptographic algorithm. We shortlisted 5 AEAD-based ciphers. We performed experiments in 3 different hardware configurations using microcontroller with processor speed 16 MHz, 48 MHz, and 84 MHz. The chart shows the execution time of each algorithm. In all hardware configurations, ChaCha20 Poly 1305 takes significantly less time than others. Another challenge was to select secret key. The asymmetric key technique is significantly slower than symmetric key and consumes more resources. Thus, we selected symmetric key technique. The symmetric key uses a single key for encryption and decryption. A new key can be generated and shared among all ECUs to provide strong security. However, key generation and sharing between ECUs is complex as CAN is a multi-class based network and there is no central authority. And if we use the same key throughout the lifetime of vehicle, it can get compromised. Therefore, we generate a session key at starting of a vehicle. We use the session key for a limited time, so even if it gets compromised, it can bypass the security measures for only one session, as it changes every time the vehicle starts. Another challenge was deciding the size and transmission process of message authentication code. A MAC with bigger length can provide better security. However, the size of CAN frame is limited, and the use of multiple frames will not only increase the traffic of the network, but also the communication delay. CAN frame has a 15-bit CRC field that provides error detection support. The proper solution can ensure data accuracy using MAC. This is why we replace CRC field with MAC. The replacement allows keeping the network traffic same as standard CAN, and the receiver does not need to wait for MAC to arrive by a separate frame. Two related work have been found that have taken the similar approach. Here, the probability of guessing MAC is 2 to the power minus 15. In other words, an attacker requires more than 32,000 attempts to guess the MAC. That we believe is not feasible considering the limited resources available in ECUs. We analyzed the design to verify standard CAN and AutoSAR compliance. The CAN protocol is standardized under ISO 18981. The compliance with standard protocol gives flexibility of integration with most of the existing systems. A security solution should be able to run on existing issues and networks to achieve the standard CAN compliance. Some security solutions require hardware changes in transceiver. Our solution does not require any hardware modification, so we can say that it is compliant with standard CAN. To verify the compliance with the AutoSAR standard, we studied the release document specification of secure onboard communication. According to the specification, sending and receiving nodes require to maintain freshness value to provide message freshness. It is not mandatory to add the freshness value to the payload. However, it must be considered during the MAC generation. In our work, Chacha20 Poly1305 maintains an internal counter to ensure freshness. So we can say that this work is AutoSAR compliant. The table shows the profiling required to integrate the solution with AutoSAR. To simulate an in-vehicle network consisting of multiple issues connected by CAN bus, we connected multiple Arduinos. However, Arduino does not have the capability of CAN transmission. So we installed CAN bus shield on top of Arduino. The CAN bus shield is embedded with CAN controller and a CAN transceiver. For validation purposes, we did some security experiments and attack protection analysis. Our experiment shows that this work ensured data confidentiality, integrity, and authenticity. Also, our attack protection analysis demonstrates that our work protects the network from eavesdropping, spoofing, replay, man-in-the-middle, and remote attacks. To evaluate the framework, we have considered 4 criteria: communication overhead, bus load, deployment cost, and compatibility. Communication overhead is very important as the communication must be real-time. In a situation of a probable accident, even a few milliseconds can make difference. Based on the hardware configurations, the communication delay of our work can be reduced to 0.07 milliseconds. The next one is bus load or network traffic load. Many issues are getting installed in a vehicle, and if the security measures increases the load of the network, it will have an impact on message processing latency. Some existing work transmit additional messages to transmit authentication code. We use CRC field to transmit the MAC. This is why additional messages are not required in our case, and the network traffic stays unchanged. Deployment cost is important as there are already huge numbers of vehicles are in the market. Some existing work install dedicated ECUs for security purpose. It is costly and may be not feasible for already manufactured vehicles. Our solution can be integrated by software updates only, so we claim that it has low deployment cost. We also verify if it is compatible with the code specification of CAN protocol. Some existing work use CAN+, which provides transmission of additional bits by modifying the communication process. We only replace the CRC field as Mac can provide error detection support. So we say that our framework is highly compatible with the CAN specifications. We also compared our work with some existing cryptography-based solutions as the table shows. It includes two other works, OOCAN and TAOCAN, that ensure confidentiality, integrity, and authenticity, but both have high communication delay. vCure, CACAN, and TCAN outperform our work in terms of overhead, but they do not provide confidentiality, integrity, and authenticity. Comparing with other work, we can say that with reasonable overhead, our work provides strong security. It does not increase the network traffic, has low deployment cost, and high compatibility. In summary, the involvement of technology in vehicles has opened the in-vehicle communication network to the cyber world. There is no built-in security measures in CAN, and attackers can gain access to the in-vehicle network by exploiting the vulnerabilities of it. We classified the existing security solutions for CAN in terms of security enforcement procedures. The classification can help researchers selecting an approach depending on security requirements. We also proposed a lightweight distributed authenticated encryption framework. It protects the network from the most common form of attacks. The comparative analysis shows that our approach suffers from less overhead compared to the solutions with similar security measures. It does not increase network traffic and can be integrated with software updates only. One of the limitations of this work is the cryptographic algorithm requires a secret key, message counter, session ID, and session key. These values have to be stored, which consume memory storage. Besides, we generate a session key from pre-shared secret key. If an adversary compromises a session key, it can bypass the security measures for that session. Also, CAN is a broadcast-based network. All the ECUs receive the transmitted messages in network. So, the counter increments upon receiving every message, which keeps all the ECUs synchronized. If an ECU somehow does not receive some messages, then it cannot synchronize with the network. A secret key generation, sharing mechanism, and a synchronized protocol can resolve these limitations, which we consider as a future work. That is all. Thank you for your attention.
Hello everyone, thanks for joining us virtually. My name is King Tuan Zhao, a PhD student from the Ohio State University. Today, I'm going to present our study on the accuracy of measured proximity of Bluetooth-based contact tracing apps. This is a joint work with my colleague Haobang Wen, my advisor Dr. Zhiqiang Lin, our collaborators Dr. Dong Xuan and Dr. Nes Schroff. The COVID-19 pandemic has widely spread across the world. As of August 2020, there are more than 25 million infected cases and over 840,000 deaths globally. Also, it is the reason why we meet here virtually. Since COVID-19 won't disappear shortly, practical techniques must be used to fight this pandemic before vaccines are available. As an infectious disease control strategy, contact tracing is such a practical technique that helps to identify people who have been in close contact with contagious individuals. However, previous contact tracing is performed manually. That is hard to scale to large and rapid moved populations, and also may result in delays. Therefore, numerous digital contact tracing systems have been recently developed and deployed by using a variety of sources, such as locations measured from Wi-Fi hotspots, GPS, and Bluetooth Low Energy, BLE. Among these digital techniques, BLE has emerged as a promising solution due to its ubiquity. Almost everyone holds a smartphone today. Its availability, nearly all smartphones have enabled Bluetooth by default. And most importantly, it's privacy preserving that no real location is involved. In addition, for COVID-19, a close contact refers to a user who has been within 6 feet, 2 meters range of a contagious individual for more than 15 minutes, according to the recent CDC guidelines. Using BLE for contact tracing between smartphones is a complicated process. First, a BLE-based contact tracing app should be installed, and the app will periodically generate a random token, a temporary ID for each user as identifier. And the phone constantly broadcasts this ID to nearby smartphones. Meanwhile, each phone also keeps scanning signals that are from other smartphones. When two smartphone users encounter each other, the apps on the two phones will automatically exchange the necessary information to record these contact events, such as temporary ID, the timestamp, and most importantly, the data used for distance measurements. And such contact events are stored locally. When a user is tested positive, the app will immediately inform all other users who have close contact with this individual. This exposure notification mechanism is implemented differently according to the different architectures, centralized architecture or decentralized architecture. In a centralized architecture, the infected person is asked to upload the recent contact events to the central server, and the server analyzes those events to identify all other users who have been exposed to this individual, and notify each of them according to the user contact information, cell phone numbers, that is usually collected at user registration. If in a decentralized architecture, the infected person who also has to upload the recent contact events to the central server. Meanwhile, all users will synchronize its own data with the database on the server periodically. Whenever a synchronization is accomplished, the app locally checks its own contact events against the updated data to determine its own risk of infection. Since a contact is recognized by the time duration, 15 minutes, and the distance, 6 feet, the time duration can be obtained by using timestamp, and the distance in BLE contact tracing is measured from the RSSI, the received signal strength indicator, from each other. It is worth mentioning that every BLE-enabled device can measure the RSSI, and in theory, the RSSI is proportional to the distance of signal transmission. However, in practice, RSSI value is unreliable and can be affected by a number of factors that can come internally, both hardware and software configurations, or externally, such as radio waves interference and obstacles, such as the human body, when putting a phone in a pocket. For example, the hardware, the TraceTogether team in Singapore has conducted an experiment to measure the strength of signals emitted by different phone models from 2 meters away in an anechoic chamber. Here's what they had. We can see a huge variation between models, up to 20 dBm, that may result in a 10-meter distance difference. With respect to the software, let me show you a real example. This app, Stop Corona, is released by the government of North Macedonia. From this figure, we can see that the app configures its broadcasting behavior by setting its advertising mode as balanced, whose broadcasting interval is 250 milliseconds, and sets its level of transmission power as high that uses the strongest power to emit signals. In addition, we also uncover how it calculates the distance. It only uses the RSSI value and this formula to calculate the distance. Interestingly, the original formula is like this, and the 3 coefficients are constant values that are used to tune the accuracy for different hardware. Since this app only uses fixed values for coefficients, and even not using transmission power, it will be challenging to have an accurate and reliable measured distance between users. Motivated by this example, in this study, we wish to understand the current practice of BLE-based contact tracing apps to obtain proximity. Specifically, we'd like to focus on the usages of BLE configuration APIs in mobile apps to understand its broadcasting behaviors, as well as the proximity-related data in advertising packets. In addition, given a variety of affecting factors, we also wish to understand how these apps respond to them by uncovering which type of data has been collected and how such data is used to have the proximity. It is a bit challenging to obtain these BLE-based contact tracing apps because there's no central repository for these apps, and directly searching keywords on app stores such as Google Play can hit the region restriction policy that an app is only available in certain regions that limits the number of apps that are returned by its searching engine. In the end, with our best effort reviewing news reports and combining lists made by other groups, we have identified 20 BLE proximity tracing apps. In addition, there are 19 apps support both iOS and Android. 9 apps are centralized and 6 apps are decentralized. And the remaining 5 apps have not officially declared their architecture. Let me show you more details. First, broadcasting behaviors. The level of transmission power. There are totally 4 levels. We have identified 8 apps that specify the highest transmission power, 6 apps that specify it to be medium, 4 apps that set themselves as low level, and 2 apps that apply the lowest power. Next, advertising mode, which is the broadcasting interval. There are 6 apps that are set to broadcast advertising packages with minimum intervals every 100 milliseconds. 6 apps that use the balanced mode that every 250 milliseconds. And 8 apps that apply the lowest power mode that broadcast every second. And all these apps intend to broadcast infinitely until being forced to close. In addition, with respect to the proximity-related data, the level of transmission power, there are 10 apps that have included this information in advertising packets, while the other 10 apps do not. Next, data collection. From 20 apps, we have uncovered the data collected for proximity measurement from 16 apps. The rest 4 apps use native code and reflection to collect data, and we leave them in the future work. We have classified such data into 3 categories. First, the most interesting one that, in addition to use BLE, there are 3 apps that even collect GPS coordinates for measurements. When coming to the BLE proximity measurement data, all these 16 apps collect RSSI. Well, there are 4 apps only collect RSSI, even without the transmission power. Moreover, there are 9 apps that collect the transmission power and 5 apps that collect hardware information, such as phone models. Finally, the measurement formula. Uncovering this formula from contact tracing apps is challenging. First, in a decentralized service, the formula is supposed to exist on the server side, whose code is inaccessible to us. Additionally, in a decentralized service, it is also non-trivial to uncover them from mobile apps because of a variety of obfuscations on the code. In our study, we have identified 4 out of 6 decentralized apps use obfuscations ranging from variable and method renaming to reflections. In the end, with our best effort, we have uncovered the formula from 3 apps. Interestingly, they use the same distance measurement model as this one. In particular, 2 apps use the Beacon library, which has tuned the coefficients for 4 phone models, and 1 app, as our motivating example, use fixed transmission powers and coefficients. Discussion. These apps are designed to provide the same service but act differently. There are several interesting observations. First, the BLE broadcast behaviors are highly inconsistent. While the impact of different behaviors on proximity measurement is still unclear, and it is one of our future work. Second, only a few apps consider affecting factors from hardware specifications, such as collecting phone models, while such tuning is quite limited. The last one, from the data that these apps collected, there's no evidence indicating that external factors have been considered. Therefore, a practical and effective solution to improve the accuracy would be tuning the RSSI for different phone models because of their significant impacts on the robustness of the RSSI value. Fortunately, some groups, such as OpenTrace groups in Singapore, have started conducting experiments and collecting data for this tuning. However, only a limited number of phone models have been involved. More efforts are needed. Another suggestion is to involve environmental factor detection algorithms in proximity measurement. Our related work includes the recent proposed mobile contact tracing protocols and their security and privacy studies, and the analysis of COVID-19 apps. For the sake of time, I'm not going to talk them here in detail. Please refer to our papers. Thank you for your attention. Now I'd like to answer any question you might have.
Hello, my name is Tyler McDaniel, and I'm going to be talking today about the Maestro attack. First, a little background on interdomain routing. The internet is a confederation of many smaller networks called autonomous systems that are under unique administrative control. And these networks use something called BGP, or the Border Gateway Protocol, to communicate routes to one another. Routers in neighboring ASs use BGP to exchange routing information across AS boundaries. BGP is a path vector protocol with policies. And what those policies mean is that local network operators, AS operators, can apply a very flexible set of policies to choose a single best path to a destination prefix from all those that it's been advertised. So how does this work? So starting at the very left of this diagram, AS1 originates a prefix 1230. And the AS path at that point is only 1, and what that means is 1 is saying I'm hosting this block of IP addresses. Its neighboring ASs, in this case AS2 and AS3, hear this BGP update, and maybe they install this route to the prefix advertised by AS1, and they prepin themselves to the AS path. And what this means is that they're going to serve as a hop on the path to this prefix. So AS4, the shared neighbor of AS2 and 3, receives the advertisements from both AS2 and AS3, and so it has a decision to make. The local network operators of AS4 have to decide whether they want to send their traffic over AS2 or AS3 to this prefix hosted by AS1. And in this case, their policies result in selecting the route over AS3, and AS4 exports that route and only that route to its neighboring ASs. So it again prepends itself to the path and propagates it just as ASs 2 and 3 did. Economic relationships are central to BGP. These fall into two major categories: peering relationships, where ASs agree to transit traffic between them without compensation. And then there's a provider-customer relationship, where a customer AS pays a provider to transit traffic to remote networks. And these types of relationships give rise to something called valley-free routing. So if you look at the diagram on the right, where providers are higher in the diagram and customers are lower, if the AS marked leak dest originates a route to its provider, and that provider exports the route to the red AS here in the center of the diagram, that AS has learned about the route from a provider. An economic incentive is going to dictate that that route export from the red AS is limited to its customers. If you want to see a reason why, consider the case where the red AS exports the route to its other provider in the top left of the diagram. In that case, that red AS is agreeing essentially to pay one provider to receive traffic and pay another provider to deliver it to the leak destination. And that's why this term leak is in the diagram, because this is something called a routing leak, when an AS exports a route in a way that maybe is against its economic incentive, or a route that was meant to be kept internally. So valley-free routing means essentially if I learn about a route from a customer, I'm going to share that route with all of my neighboring ASs. But if I learn about a route from a provider or peer, a route export should be limited to only my customers. And there's another important term here, which is the customer cone. The customer cone is simply all the direct and indirect customers of an AS. So an AS's customers, its customers, and so on, all the way to the fringes of the internet. So BGP poisoning is an important primitive that we use in this work. So this is a diagram kind of like the interdomain routing diagram before. AS1 is going to originate a prefix. The difference here is that AS1 is going to include an AS3, on the AS path of the original advertisement. And so AS2 is going to receive this advertisement, and it's going to treat it exactly as it did in the first diagram and prepend itself and export the route. However, AS3 is going to see itself on the AS path of the advertisement, and this is going to trigger something called BGP loop detection. And this is a feature that's meant to prevent routing loops, but AS3, when it sees itself on this path, is going to filter the route, and it will not install or export it. The result is that AS4 only hears about this path from AS2, and so it no longer has the choice between these remote networks for transiting its traffic to AS1. And essentially what we've accomplished with the poisoning is we've selectively prevented route installation at a remote network. And this has been used for topological discovery and even DDoS defense, but we're going to use it for more nefarious purposes. And that nefarious purpose is a link flooding attack. A link flooding attack is a DDoS that, rather than targeting a specific end host or service, it targets part of the internet infrastructure, such as an inter-AS link. So this is a little diagram. These blue ASs are maybe they're big telecoms in the core of the internet, and there's a link between them that serves many of these black victim ASs. Maybe there are some bot hosting ASs, the red ones, and they can find traffic for their bots, maybe between bots or to decoy destinations such that the traffic transits this target link. It's correlated there. And what happens is that link is degraded as the bot traffic drowns out benign traffic, and we've accomplished this link flooding attack. So the traditional example in the literature is core melt or crossfire, but there are variations of this, but essentially we're targeting an infrastructure link with a DDoS. Why is this possible? Well, because BGP security is kind of an oxymoron. BGP is a very old protocol dating back from the 90s, and it assumes that all speakers are honest. There's no widespread tying of cryptographically of origins to the IP prefixes that they are allocated and authorized to originate. There is something that's in partial deployment called RPKI to help with that, but again, it's still limited, its deployment. And then there's no cryptographic hardening of routes. And what this means is that we routinely suffer from major routing disruptions. These fall into two main categories: leaks and hijacks. Leaks are where an AS exports a route that is meant to be kept private or shared maybe only with a subset of its neighbors. And then hijacks, where an AS originates a prefix that it has not been allocated. Maybe it's someone else's IP prefixes. These generally result from misconfigurations, but they also open the door to these really nasty attacks that leverage the problems with BGP. For example, in 2018, there was a DNS hijack, and some very sophisticated criminals hijacked some of Amazon's IP prefixes that contained its authoritative DNS, and this hijack announcement spread to some of the internet, including Google's DNS service. And so what happened when a victim entered a target website, in this case myetherwallet.com, the root DNS, instead of reaching out to Amazon's authoritative DNS at the correct destination, instead went to another fake DNS service hosted by the criminals, and this resolved to the IP of a forged site that looked like myetherwallet.com. Of course, the certificates did not match, but users clicked through those warnings, of course, and they input their login info, allowing the adversaries to steal over $300,000 of cryptocurrency in a matter of hours. So we can see that adversaries are willing to leverage these problems with interdomain routing. And we ask, what if the adversaries have a different motive? What if instead of trying to steal funds, what if instead they were trying to create disruption or achieve some other effects? And those lead to our primary questions. First, we want to know how internet routing choices, how the interdomain topology limits link flooding attacks or influences link flooding attacks. And then we want to ask how a routing capable adversary could defeat these limitations, maybe to enhance a link flooding attack or to target links that would be shielded by routing choices. So for the first question, the limitations of LFAs, prior work on link flooding attacks either selects target links based on bot paths, so the adversary selects targets based on what they know they can hit, or the work assumes that arbitrary links can be targeted by a botnet. But recall that network operators, not hosts, choose paths, so bots cannot choose the path that their traffic takes to any given destination on the internet. This is a choice that's made by the network operator that hosts the bots. To explore these things, we're going to use a couple of metrics. First, BGP betweenness, and this is simply the number of times that an inter-AS link appears on installed routes between ASs. This is meant to capture relative usage or the importance of a link. And then we have this other metric, flow density. that captures the percentage of bots that have a path to another bot or even another decoy destination that crosses the target link. And this gives us some notion of vulnerability. So these again are both link metrics. Betweenness captures usage and flow density captures vulnerability. And what we want to do is build a simulated internet topology. And so we did this with Kaida's AS relationship data set. This is the state-of-the-art inference about the economic relationships between ASs. And the simulator uses this information in a simplified BGP decision process to build an internet-level topology. And then we're going to map IP data from prior work for major botnet families to the ASs that are hosting them. So step 1 builds a topology, an AS-level topology, and step 2 locates bots within that topology. And then third, what we want to do is analyze the exposure of each link in that topology to these botnets. So these are our results, and on the x-axis for both of these plots we have flow density, so that measure of vulnerability, the percentage of bots that can attack a certain link. And then on the y-axis we have BGP betweenness, which captures usage, how many ASs are using a link, and each dot is a link. It locates, these graphs locate links on this vulnerability and usage graph. So on the left chart is if we allow bots to flow traffic to any destination, and the right chart is if we allow bots only to transit traffic between themselves. And these roughly correspond to prior attacks in the literature. And what we find is, as expected, in the bottom left of these graphs, there are some very little trafficked links that we can't flow much of the botnet over. But the more interesting thing is what happens towards the top of the graph. We see that there's a wide variance in both of these cases. So there are some very well-trafficked links that are very exposed. They're close to 100% flow density. But then there are also a lot of very important core links, some 10 to the 6, 10 to the 5 betweenness links that are not targetable by the majority of botnets. So this is an important result, and it really shows that interdomain routing choices can shape which of these links are exposed to botnets. So we asked ourselves our second question: how can a routing capable adversary overcome these limitations to expose previously shielded links or to enhance flows over already vulnerable links? And that's where the Maestro attack comes in. So the Maestro attack involves an adversary with routing capability at some adversary AS. Really the adversary only needs one edge router in that AS and a botnet. And the adversary is going to target generally provider to customer inter-AS links. And how this works is the adversary directs its botnet to flow traffic towards the adversarial controlled AS, and then it uses traceroute information from the bots to see the AS level paths that the bots are using for their traffic, and then it's going to use that information to selectively poison certain ASs to channel the flows from the bots over certain inter-AS links. So if you look in the diagram here, where the purple ASs here are ASs hosting bots, and the solid black lines show how their traffic is flowing through the topology prior to the attack. Maybe some of the traffic is being transited over 4.7, some of the traffic is being transited over 6.9, but suppose the adversary wants to collapse all the flows over link 5.8. Well, the adversary can use traceroute information to determine what ASs are transiting traffic for its bots, and then it can use poisons to cause, essentially block inbound flows over those ASs, over ASs 4 and 6 in the case of this diagram. And what you essentially get at that point is a channel DDoS towards AS10, the adversary controlled AS, where traffic is concentrated on this one target link, 5.8. So essentially we're DDoSing towards an adversarial AS, and then we're using poisons to block the available routes for that traffic to collapse it onto a target link. So how are we going to evaluate the attack? We use the same simulation framework from the LFA limitation experiments before. We have some method of selecting links and adversaries to attack those links. And then we're going to simulate poison advertisements for each link adversary pairing. We're essentially going to simulate the attack, and then we're going to measure the gain in flow density that we achieve from the attack. So if you look, these are both CDFs, and with flow density on the x-axis over all the different adversary link pairings. And so the left diagram is the case where we randomly select adversaries and links from the topology and try to execute the attack. The solid lines are pre-attack flow density, and the dashed lines are post-attack flow density. So our gain, the adversary's gain in this case, is the space in between these sets of lines. And what we see is that in the random case, this doesn't work very well. But these experiments gave us insight into what the structure of successful attacks looks like. And we extracted some of those successful attacks and ran them on the right. And these are attacks where the adversary is positioned as an indirect customer of the target link. And what we see, the blue line is pre-attack flow density, the orange line is post-attack flow density. And what we see is in this, with this advantageous positioning, the adversary is able to achieve a substantial effect on flow density. So before the attack, most links have 10% or fewer of the botnet that can flow over the link, and this is for the Mirai botnet. But we see that after the attack, most links have a 40% or greater flow density flowing over the link. So an entire third of the botnet is added to the link flooding attack as a result of the Maestro. So we have some other graphs in here for exploring success conditions, and these mostly show two things. So the heat map on the left shows that as the closer the adversary is to the target link, if it's a direct customer, we can expect the greatest effect. And as we move away from the target link, that effect diminishes. Our ability to steer traffic over the link diminishes. The violin plot on the right shows gain in flow density on Y, and then there's a violin plot of the distribution of links at any specific gain level. So what we see is that for customer provider links, we had very little success in boosting flow density. But in the provider to customer case, we had much better success. And the reason for this is those economic relationships I talked about before. So as the adversary, as the customer of the target, we can expect our poisoned routes to spread more freely throughout the topology because we're sharing them with providers, and those providers, because we're a customer, are sharing them with all their connections, and so on. So this is an important characteristic in determining attack success. So we also built an internet proof of concept to prove the attack in practice would work. And we used the peering framework to issue poison advertisements, and we used ripe atlas anchors to serve as our notional botnet. So you can look in the paper for all the details of that. But essentially, in both of the cases we tried, we were able to achieve substantial increases in flow density, at least 2x. And so that was important for showing that the attack was feasible in practice. We also explored some vulnerability and mitigation concepts. So we identified some potential mitigations for the attack, including filtering all poison routes. That's problematic because some people do use poisoning for benign traffic engineering. We also talked about selective filtering, where some poison routes are filtered. Monitoring, where ASs monitor the advertisements of their customers to look for this kind of behavior. And then, of course, there's next generation solutions like new interdomain architectures or SDN-based defenses. So we did do some simulations on the effectiveness of poison filtering at specific locations. Flow density is on X on this diagram, and then it's again a CDF on Y. And what we found was that filtering at very important ASs, for example, Tier 1 ASs, the 19 Tier 1 ASs, could have a substantial, almost 50% impact on limiting the effectiveness of the attack. So that was a good result. And then also, if enough ASs that are less well positioned also filter, we could have a good result there as well. So the takeaways: LFAs cannot hit arbitrary links on the internet with full force of a botnet. But we can overcome partially these limitations with selective BGP poisoning. For future work, we could explore other routing primitives for controlling flows, and this is motivated by, in the proof of concept, we ran into some cases where these poisons were being filtered, and we explored that further in another paper, a PeerLock paper that's going to appear at NDSS. So if you're interested in this, there's a PeerLock paper at NDSS 2021 on this kind of filtering. But those other routing primitives could include no export communities or intentional route leaks. And then could we use multiple prefixes and multiple target attacks to isolate, for example, an entire geographic region, as in the crossfire attack? That's something we want to explore as well. So thank you. That's my talk, and I'll take any questions.
Hello, my name is Quinn, and today I will present our work on misreporting attacks in software-defined networking, where we show how, depending on untrustworthy reporting and making control decisions here in the context of load balancing, can lead to fundamental security failures. This is joint work with myself, Patrick McDaniel, Thomas Laporta, Ming-Li Yu, and Ting He from Penn State University. With increasing dependence on services that can be offered anywhere and at any time, there's increasing amount of complexity in managing the networks that comes along with those demands. For example, managing segmentation to ensure that we isolate client traffic for security, managing quality of service to ensure that we meet bandwidth requirements for customers, and also managing mobility to ensure we maintain service for mobile users becomes difficult. Traditional methods for providing these services are inefficient for cloud-scale networks for many reasons, including the heterogeneous set of software suites running on all the devices, along with their own command line interfaces, proprietary software lock-in, which sometimes makes it difficult to tune software towards specific provider needs, and also the distributed nature of devices and the protocols used for implementing different services, which all make for a very manually intensive task when managing different services, especially for larger networks. Enter software-defined networking. Software-defined networking, or SDN, is characterized by the separation of the control and data planes, where we can implement different network functions such as firewalling and load balancing, among others. They run as applications atop the controller and orchestrate specific functionality via flow rules. And this work will focus specifically on load balancing. In SDN, load balancing is commonly divided into two components. First, we have the application logic, or the load balancing algorithm, which runs as an application atop the SDN controller, and then enforcing of the load balancing decisions is done by installing appropriate flow rules at the network switches. Here, the network switches are employed to report traffic loads, which in software-defined networking come in the form of switch statistics under the OpenFlow protocol. The switches are employed to report traffic loads to the controller application in order to decide where to route incoming flows. Newly arriving flows into the network by default are forwarded to the controller, where the load balancing algorithm is executed and a flow route is installed to the network switches. Now, while this offers scalability and reliability benefits, because the load balancer can be scaled horizontally at the controller, this separation of control and data planes and the reliance on collecting faithful information from the network switches creates an opportunity for an adversary who's able to compromise a network switch to misreport the traffic loads in order to influence the load balancing. So the load balancer depends on accurate traffic loads in order to perform well, but if an adversary was to underreport the true load that's passing through some switch port, then they can influence the controller to draw more traffic through the switch and away from other switches and therefore servers in the load balancing pool. In this work, we focus specifically on underreporting the true load in order to draw more traffic toward the compromised switch for eavesdropping purposes. While prior work has addressed the problem of misreporting in other contexts, such as link discovery, host tracking, among others, here we address the problem of misreporting in the context of load balancing. We focus our efforts on 4 widely used load balancing algorithms, which are implemented in the widely used SDN controllers Open Daylight and Floodlight. The load balancing algorithms are firstly the least connections algorithm, where a flow endpoint is selected based on the number of currently active connections it's serving. Secondly, the least loaded algorithm, where a flow endpoint is selected based on the amount of load in bytes that it's currently serving, along with their weighted counterparts. The threat of misreporting is enabled by the fact that the load balancing algorithms rely on some form of least X selection based on the traffic loads given in the load reports. And we note that in ongoing work, we are looking at misreporting under more complex load balancing algorithms. Our hypothesis is that we can arbitrarily control the volume of traffic flowing through a compromised switch by manipulating the values sent in the traffic load reports. Toward this goal, we developed two methods for attacking the load balancer. One, called the max flooding attack, where we try to draw as much traffic as possible through the compromised switch. And two, the stealthy attack, where we introduce a method for estimating traffic characteristics in order to draw specific target loads through the compromised switch. We take a queuing theoretic approach in modeling the attack, and we develop flexible algorithms that allow the adversary to tune the attack parameters towards specific adversarial goals. We begin with the threat model before providing an overview of the attacks. We first assume that switches report aggregate traffic statistics, in other words, port level statistics, to a trusted load balancer, which uses the load reports as a proxy for the load seen at the connected servers. Then we assume that of the switches that make up the load balancing pool, one may become compromised. In general, the adversarial goal is to control the volume of traffic flowing through the compromised switch by misreporting the traffic loads. The purpose of drawing more traffic may be to perform larger scale eavesdropping on unencrypted traffic or perform traffic analyses on the encrypted traffic, which have already been established as significant threats in modern cloud networks. If there's a large enough volume of traffic in the system, where the system being the client traffic destined toward the load balancing resources, then the adversary can also cause congestion at the endpoint connected by the switch port, but not cause denial of service to itself. The adversarial capabilities here are limited to only recording load reports at the compromised switch and also sending misreports. And we focus on underreporting here to draw more load, but are considering overreporting attacks to, for example, deny service to the connected endpoint without having to drop traffic in ongoing work. The challenge with misreporting lies in attaining the adversarial goal while also managing the risk that the adversary is exposing themselves to through misreporting. And this leads to the following research questions. 1. How often must the adversary misreport in order to accomplish their goal? 2. What value must they misreport to in order to have a successful misreport? And 3. To what extent can an adversary control the volume of traffic by misreporting? So to what degree, to what accuracy can the adversary achieve their goal? To answer these research questions, let's first start with a case study on network traffic behavior observed in modern cloud and data center networks. Studies of modern data center and cloud networks have identified two distinct network traffic patterns among different cloud services. The first consists of a majority of small in bytes and short in seconds flows that exist only momentarily in the network. Looking in the figure on the top of load reports collected once per second from a single switch in the load balancing pool, we observed that this traffic pattern is characterized by momentary load spikes, where a burst of flows would arrive at the switch and expire within just a few seconds. And here we observed that each load spike corresponded to a time instant when the switch reported the minimum load to the load balancer. And so here, to draw more load through the switch, the adversary must misreport to induce more load spikes. The second traffic pattern consists of a majority of relatively longer and larger flows that persist in the network for several seconds or minutes, for example, for applications like video streaming. Looking in the figure on the bottom, we observed that this traffic pattern was characterized by a more stable load over time. where each time a switch would report the minimum load, a set of long-lived flows would be scheduled to be routed through the switch toward the server. Therefore, to increase the volume of traffic passing through the switch, the adversary must misreport to increase the average number of flows actively sending traffic through the switch at any given time. With this, the adversary then specifies a target utilization row tar that has an associated lambda tar in bits per second that they intend to draw through the switch port toward the server. From here, the adversary must calibrate two parameters to draw the target utilization. L bar is the average load, the meaning of which differs slightly depending on the considered traffic pattern, and it's used to determine the frequency at which misreporting is done. The second parameter, delta, which is the misreported amount sent to the load balancer, determines by how much the adversary misreports by, and the choice of which will affect the success rate of misreporting. In other words, how successful the adversary is at sending a misreport that is the minimum value reported by all of the switches. We introduce heuristic methods for calibrating both parameters. We first let M denote the number of misreports required in order to achieve the goal. We observed previously that time instances where a switch reported the minimum load corresponded with a load spike, and therefore a single successful misreport, if being the minimum value, therefore corresponds with a single load spike. Then the required number of misreports to draw the target load through the switch port can be approximated with knowledge of the amount of load contained in a single load spike, or its amplitude. If in the context of short flows, we let L bar represent the average load spike amplitude, then if we divide the total desired load over the attack window by the average load spike size, we can determine the required number of misreports to draw the target load through the switch port over the attack window W. In the context of long flows, a single successful misreport here corresponds with a set of long-lived flows being scheduled through the compromised switch. Therefore, our heuristic approach here is to misreport consecutively in batches in order to have more of these flow sets being scheduled through the switch whose lifespan nearly overlaps in time. On the left, dividing the target load by the average load seen over time determines the number of consecutive misreports that must be sent in each batch. And if we consider the flows to last on average t-long seconds and misreport b times at the beginning of every t-long second time slot, we compute the number of misreports that must be sent over the attack window. Given the attack model, in order to compute the number of misreports that must be sent, in the context of short flows, we take a heuristic approach to detecting load spikes to compute the average load spike amplitude. For example, by assuming any load higher than the 90th percentile load will be considered a load spike, and taking the average magnitude across a configurable number of detected load spikes. In the long flows case, the adversary would record a configurable number of observed loads over time and take the average. Before sending the misreports, the last step is to calibrate delta, which is the actual value sent in the misreport to the load balancer. The assumption here is that the adversary at the compromised switch can use their cumulative probability distribution as an approximation for that seen at other switches and intelligently select a load value that has high probability of being the minimum of all values reported by the switches. The goal here is to find a value to misreport to, and naturally there's a trade-off between misreporting success and detectability, where there is more risk in misreporting by a larger amount to a lower value, and vice versa. Here the adversary would select a cumulative probability U with an associated load value in bits per second, UL, as the upper bound load to which they misreport to, and select a value within the range 0 UL that provides a high probability of being the minimum reported load. And equivalently, a minimal number of switches also expected to report within that load range. With the two parameters L bar and delta calibrated to determine the number of misreports that must be sent and suitable load values to misreport to. Then, in the short flow scenario, the adversary would misreport randomly m times, and in the long flow scenario, misreport in batches of size b for a total of m misreports. And we note here a special case misreporting attack called the max flooding attack, where the adversary directly sets delta to 0 to draw as much load as possible through the switch and toward the server. We now evaluate the effectiveness of our attack in a variety of different settings using the Floodlight SDN controller. Here we consider the 4 common load balancing algorithms that we described, and we consider both traffic types for a pool size of 10 members. The key metrics that we measure here are 1, the damage, which is the additional amount of load drawn, as well as the potency, which describes how much additional load per misreport the adversary was able to draw. In terms of attack effectiveness, we found that with the max flooding attack, when the adversary directly set delta to 0, that they were able to draw more than 700% additional load through the switch, or nearly 85% of the load in the system, at a success rate of 100%. And further, we observed that each misreport resulted in approximately 2.5% additional load being drawn through the switch. For the stealthy attack with a target load of 3 times that observed under normal conditions, we found that when misreporting to the bottom 1th percentile of loads over a reconnaissance phase of 30 minutes before sending the misreports, that the adversary was still able to maintain a more than 90% success rate and draw a volume of traffic to within a 12% error of the target. We observed similar results for the long flows, and none of the load balancing algorithms proved to be more robust against the misreporting attacks than the others. In terms of the effects on network performance as a function of the target load and therefore the misreporting rate, we first modeled the output switch port toward the server as an MD1 queuing system following prior work, and the key takeaway here is that the throughput decreases rapidly with the target utilization and also the number of misreports. And further, our analytical model approximates the shape and scale of the conditions observed in our experimental network and can therefore be used for several purposes, including both analysis for building defense systems as well as planning attacks. In summary, we show that an adversary at a compromised switch can very effectively control the volume of traffic flowing through the switch by misreporting traffic loads to a load balancer. While here we consider 2 distinct network traffic patterns independently, which are representative of load balancing pools that might serve a single service, in ongoing work we're investigating the effectiveness of misreporting traffic loads under mixed traffic conditions. Nonetheless, we also show here that load balancing fairness is very sensitive to misreporting, and equivalently the misreporting potency is strong, as we've demonstrated, for example, that an adversary can increase the load drawn through the switch 3 times over by misreporting 30% of the time. And finally, the attacks can be feasibly mounted in real networks with a simple change to the OpenFlow agent binary running on the SDN-enabled switches. And while recent advances in SDN-based anomaly detection have partially addressed this problem, the approaches are not designed to detect this attack. For example, the state-of-the-art detection system Sphinx relies on trusting edge switches to detect inconsistencies along flow paths, and it only operates at flow level, whereas load balancing is typically done at port level, and therefore inconsistencies cannot be traced along specific paths due to many flows combining and splitting at switchboards. Further, other defenses are designed to thwart specific attacks, for example, denial of service, link flooding, or topology poisoning attacks, and also have design constraints, for example, only monitoring host-based adversaries that render them not applicable to the proposed misreporting attacks. Therefore, important steps for future work are firstly to understand the bounds with respect to adversarial capabilities when misreporting, and secondly, to develop new detection systems that consider these intelligent adversaries in their threat models. Thank you.
Hello everyone. Today I'm here to give a presentation of our paper. In this paper, we propose an end-to-end framework to test modular detection models, including both supervised and unsupervised ones, to detect DNS covered communication in enterprise environments. As a core infrastructure on the internet, the domain name system is commonly used in all kinds of internet applications to translate easy to recognize domain names into IP addresses. Unfortunately, the DNS suffers from no vulnerabilities such as DDoS, spoofing, and other exploits. Such attacks are against the DNS itself. Therefore, they will lead to the failures or errors in DNS servers. As a result, they are much easier to be noticed by the users or the operators. Unlike those traditional attacks, DNS-covered communication is leveraged to transmit messages across the boundary between the enterprise local area network and the internet through DNS messages in a sneaky and unauthorized manner. However, the defense against DNS-covered communication in enterprise environments is still not well studied. In enterprise environments, security tools are commonly deployed to closely monitor the traffic. Such monitor systems are usually focusing on some important devices and certain traffic, for example, the HTTP traffic. Although DNS is also a fundamental system that many services rely on, some enterprise operators treat DNS as a set and forget infrastructure and do not update them from time to time with the latest security mechanisms. As a result, some attackers take advantage of this lack of monitoring on DNS traffic and choose DNS as a channel for covert communication, which is more difficult to be noticed. So first, let's take a look at how DNS works. In this figure, we show an example of a normal DNS lookup. On the left, there is a normal host queries its local DNS server about google.com, and the local DNS server then iteratively queries and relays the response with the IP address from the name server to the host. Usually, a DNS lookup has one query and one response. From the logs, we can see the query domain name and its answer. Based on this, we can know the communication between the host and the name server. In a covert communication case, attackers use DNS to establish a communication channel between compromised hosts and the remote servers. In this way, they can send the information to the outside. For example, in the point-of-sale attack, the compromised host will encode the stolen credit card information as subdomains in the domain name. And when the query arrives at the name server, which is controlled by the attacker can then easily decode the information to get the credit card information from the domain name. Such encoded data are usually long strings that are not commonly seen in normal domain names. Besides data exfiltration, some attackers also use DNS channel to transmit command and control messages. In this way, the compromised hosts can inform the attackers of their current status and receive further instructions. Here, an infected host sends a DNS query and receives the corresponding DNS response from the compromised name server, which is the CNC server. In this example, the seemingly random domain names queried are actually generated by domain generation algorithms, which is known as DGA. Such DGA domains are used as disposable reservoirs and are automatically synchronized between the compromised host and the CNC server. Based on the above examples, our intuitive idea is to apply machine learning to capture suspicious domain names based on its features. However, to deploy such a machine learning-based detection framework in the real-world enterprise is still challenging. Considering in the enterprise environments, the models should be easy to deploy and have low overheads. Besides, the performance of algorithms might be different, so the algorithms should be generic and flexible. To tackle the above challenges, we use a modular detection component consisting of multiple models, including supervised and unsupervised approaches, so that for each type of threat, the most suitable model for it can be applied. The modular design of this detection also makes it very flexible. Each machine learning model can be adjusted easily and individually for updating or modification, for example, and during the model tuning or retraining. In this paper, we propose a practical, flexible, and end-to-end machine learning-based framework called D2C2 to effectively detect various DNS covert communications in enterprises. The system can be divided into three major stages: processing, detection, and investigation. In the first stage, the system passes the raw data, extracting user demographics, DNS packages, and other network information. The second stage is the detection stage. It is composed of three modules: blacklist, feature extraction, and threat detection. Blacklist first filters the logs to effectively detect known malicious domains with low overhead. It is created from the enterprise blacklist maintained by the operators and is updated by manual investigation, feedback, and threat intelligence. Second, we extract features from the remaining logs. In summary, we choose features widely used in data exfiltration detection and DGA detection. And we also add some new features for our detectors. Not all features from prior work are used. Some of them are removed because of their low feature importance based on the evaluation feedback on a small scale of labeled data experiments. And last, we detect multiple types of threats using threat detection module. It contains several machine learning-based classifiers, and each of which is called a detector, and it focuses on one or more specific types of threats. All detectors can be modified individually according to the change of data. Results combined from all detectors will be aggregated and then sent for future investigation. In enterprise environments, the popular targets of cloud communication are data exfiltration and CNC communication. The digital domains are most common seen in CNC scenarios, while other manually forged domain names are very rare. Therefore, we designed two specific detectors, the data exfiltration detector and the DGA detector for those two main threats, respectively. Because supervised methods are more suitable in detecting no threats, the first two detectors are implemented as supervised detectors. While there will be other suspicious domains that do not fall into these two categories. So for these potential attacks left in the DNS logs, we use an extra unsupervised outlier detector in order to cover as many threats as possible. In our system, the three detectors are running in series. The first two supervised detector will detect no threats, which are majorities of all the threats. Thus, they will filter most of the threats in the data, and the remaining suspicious domains are very rare compared to the other normal domains. So such distribution of data will be suitable for the unsupervised outlier detection algorithm. In the last investigation stage, we're receiving the detection results first. The whitelist is used to flag some certain samples before they reach the operators. This is because some queries generated by certain trusted applications is similar to some attacks. Such queries are usually generated by security products from different vendors, and they are trying to send the data through the DNS channel, which may result in some unnecessary false alarms. Similar to the blacklist, the whitelist is created and updated based on enterprise operators. The remaining results are further reported to many investigations where operators and security engineers are involved to check the results. The false alerts are used as feedback to our detectors, which may trigger alteration of thresholds, which waits or even retreating of the machine learning algorithms. And the true threats confirmed are reported and visualized for analysis and displayed in our system. We evaluate our design by a real-world deployment in a large enterprise environment with substantial DNS traffic. In this enterprise, there are more than 25,000 hosts, including servers in their data center and desktops or laptops in their office networks. And some sensors were deployed in the DNS servers controlled by the enterprise to collect DNS logs in its network from all hosts. The average number of DNS logs per day is around 100 million. During the deployment, we collect over 5 billion DNS logs in the enterprise in 1 month. The number of queries is slightly larger than that of responses, about 5%. This is because not all queries has responses due to timeout, packet loss, or other kinds of network errors. We also count different types in DNS logs and list the numbers in this table. You can see that IP address queries dominate in all logs, pick up over 90%. Because in a large volume of real-world traffic, it is very difficult to get all data labeled. So before we deployed our system on the unlabeled real-time traffic, we evaluate our models on labeled historical data. And it is an aggregated trace of over 700,000 labeled logs collected in the same enterprise. It consists of historical logs previously labeled and verified by their operators. This data trace is used to evaluate all the algorithms we choose and test their overhead before the real-world deployment. Other than the two data trays for our detection models, we also introduced two lists in the system. The blacklist consists of no malicious domain names found previously or reported in takedowns, public security databases, and other threat intelligence services used by the enterprise. The whitelist contains domains controlled by the studied enterprise, security vendors, and several popular websites based on website ranking. First, we evaluate on the labeled historical dataset. We choose three supervised models: a random forest, multi-layer perception, and the support vector machine for the first two detectors. In general, all three binary classifier models used in the data exfiltration detector achieves high precision and recall, with an average F1 measure over 99%. The results in PGA detector shows that the random forest and the multi-layer perception still achieves high performance, but the performance of support vector machine is worse, especially in precision, which is only 80%. This is because some DJ domains also have differences between each other due to their different DJ families, which influence the SVM's performance. We choose two unsupervised models for the outlier detector, isolation forest and X-means. The results show that isolation forest achieves much higher performance than X-means with a precision of 85% and a recall of 92%. This is mainly because that X-means is basically a clustering method. The clustering results of X-means are highly influenced by the distribution of different patterns of samples, and the static threshold used for malware detection may not be suitable for all clusters. The evaluation results on labeled data trace demonstrate which chosen algorithms are efficient in our environment. That is, based on the above results, random forest, multi-layer perception, and isolation forest will be more suitable in the enterprise because of their higher precision and recall value in both detection of data exfiltration and the DJ domains. Another concern of a practical framework is the overhead, since systems with high overhead are not suitable to be deployed in practice, especially in enterprise environments. Thus, we also test these models' overheads by calculating the processing speeds. In the test, random forest models achieve the fastest speed with a processing speed of about 50,000 logs per second. As a reference, the average number of input DNS logs during the deployment is 1,200 logs per second. Although on this dataset, SVM has a relatively high speed, please note that the time complexity of SVM is actually much higher than others, which is n squared. So the processing speed of SVM will decrease quickly as the data size increases. Based on the performance and overhead of different methods tested on the labeled data trees, during the real-world deployment, we picked the random forest and the multi-layer perception for supervised detectors, and isolation forest for outlier detector. SVM and X-means models are not used due to their low precisions and higher overheads. For practical detection framework used in the real world, the false alert rate is also a critical metric. This is because all alerts need to be investigated by operators, and too many alerts will overrun the operators. So we presented the number of true positives and false positives per day for our models. The deployment results show that all chosen models achieve high precisions during the deployment with low false positives. Isolation forest model has the least false positives, only 2.5 per day. Random forest models in two detectors both spot less false positives than MLP models, which demonstrate that random forest models are more practical considering the investigation label cost. In this case, we only have 12 false alarms in total per day. Considering true positives, outlier detector has 29 PPs per day on average, and data exfiltration detector has more, while DJ detectors has much more. This is due to the data distribution in our data trees, in which data exfiltration-related domains and DJ domains are more common. For data exfiltration, the hosts often send multiple DNS queries for a large file or a series of multiple small files. And while DJ often generates a large number of domain names in a certain time window. As a result, considering performance, overhead, and false alarms together, random forest model and isolation forest model appear more practical in the studied enterprise environments. On average, over 4,000 logs were detected as malicious per day. We further aggregate these results based on internal hosts and remote IP addresses to reduce the investigation overhead for operators and generate visualized results. A snapshot of our visualized results on malicious domains is shown here, which is a graph displaying the relationship between hosts and the remote IPs with the different conditions in responses. DOS stands for hosts, remote IPs, and the connection state. Pages stand for DNS logs. From these results, we found that some DJ domain queries are mainly sent from 10 hosts, and the top 2 of them are local DNS servers, but the remaining 8 hosts are desktops or data servers, which are very likely to have been compromised. Many of those domains are related to CNC and botnets. However, only one of these hosts was reported as malicious by other security measures. That is, we detect at least several compromised internal hosts previously unknown to the operators of the enterprise. So, in summary, we present a practical machine learning-based framework to detect the DNS-covered communication threats. And it is an end-to-end framework which is easy to be deployed in enterprise environments and has a high flexibility. We deployed our system in a large enterprise network with more than 25,000 hosts and more than 100 million DNS logs per day. We evaluate our system based on over 5 billion real-world DNS logs during a month. The system achieves a high precision over 97%. Furthermore, we successfully detected over 4,000 malicious DNS logs per day on average with low overhead and capture real-world security issues which are previously unknown to operators, including 7 compromised hosts with multiple CNC communication attempts. And that's all, thank you. And here we have some time for questions.
Hello, we are a group of researchers from Secure and Intelligent Things Lab at Michigan State University. I am Nick Ivanov, a PhD student from Michigan State University. Together with Genji Liu and our advisor Dr. Chiben Yan, we are honored to present our work, SmartWiFi, Universal and Secure Smart Contract-Enabled Wi-Fi Hotspot. First, I will introduce the problem and the major insights behind this work. Second, I will talk about the design and unique features of smart Wi-Fi. Third, I will demonstrate our full-stack implementation of the system. Next, in the evaluation section, we will explore the parameters of the working system, and then I will conclude the presentation with a few final words. Let's get started. Public Wi-Fi hotspots allow wireless users to access internet in public places such as airports, hotels, restaurants, malls, and others. Since 2016, the number of public Wi-Fi hotspots grew from 94 million up to 454 million. And it is estimated that this number will exceed 500 million in 2022. However, most existing Wi-Fi hotspots suffer from four major shortcomings. First, classic Wi-Fi hotspots cannot provide mutual security guarantees for providers and clients. On the one hand, the prepaid Wi-Fi hotspots allow the provider to gather payment from the client, but the quality of the provided service largely depends on the trustworthiness of the hotspot. Getting a refund for a poor service or non-service often requires a time-consuming procedure of filing a claim, including uncertainty and the lack of guaranteed resolution. On the other hand, the billing-based Wi-Fi hotspots allow the client to pay after the service. However, providers have limited ability to enforce paying the bills by clients. Moreover, a client may falsely claim low quality service or non-service, which is very hard to repudiate. Second, the quality of service of public Wi-Fi hotspots is notoriously low. A typical example of such hotspot service is the hotel Wi-Fi. According to Social Wi-Fi, the three most common complaints of hotel guests are Wi-Fi is not working, Wi-Fi is too slow, and Wi-Fi is breaking up. Also, according to highspeedinternet.com, the typical speed of Wi-Fi hotspots in American hotels ranges between 1.9 and 8.5 megabit per second for both free and paid hotspots, which might be insufficient for such popular applications as gaming, video streaming, real-time work, project synchronization, and video conferencing. Another problem is that clients cannot connect to any hotspot available in physical proximity because many hotspots require the client to be an employee, student, or member of a certain organization, or be as an active subscriber of a certain internet provider, or play a certain role such as hotel guest, restaurant customer, or a flight passenger. Some hotspots are available for anyone. However, they often involve a connection procedure which requires selecting the hotspot from a list of available access points and performing a series of manual interactions involving so-called captive portals. Our research led us to profound insights that address the four problems of Wi-Fi hotspots. Specifically, we address the security guarantees issues of Wi-Fi hotspots by transferring the point of centralized trust from hotspot and client to decentralized independent party such as blockchain. We address the unreliable performance by creating dependency between the quality of service and the payment amount. We address the problem of limited access by developing a universally accessible permissionless Wi-Fi hotspot protocol. And we address the cumbersome connection procedure by designing a fully automated authentication and payment. And we call our comprehensive solution Smart Wi-Fi. Smart Wi-Fi is founded on three pillars, which are the Smart Wi-Fi system, including client, router, and smart contract, the HANSA protocol, which stands for hash chain-based network connectivity satisfaction acknowledgement, which controls sessions and guarantees fairness of payment for both the client and the hotspot, and the DAPSET technique, which stands for Dynamic User Perceived Speed Estimation Technique, which delivers automated periodic evaluation of internet connection quality. The workflow of the smart Wi-Fi system includes 8 steps, which are controlled by the hands-up protocol. First, the smart Wi-Fi router activates a hotspot. Next, the client sends the hotspot. Next, the client finds the hotspot, connects to it, generates a random hash chain, and sends the head of the hash chain to the router along with other session data. Third, the router immediately activates a temporary internet access for the user and simultaneously stores session data in the smart contract. Next, the client deposits funds on the smart contract if needed. As soon as the funding transaction is complete, the router activates a permanent internet access to the client. The funds deposited on the smart contract are not automatically available to the hotspot. To withdraw these funds, the hotspot must know the hashes on the session hash chain. The more hashes the hotspot knows, the more funds it can withdraw from the smart contract. Thus, whenever the client is satisfied with the service based on automatic DAPSET estimations, it automatically sends the hash from the hash chain to the router. This hash chain is the satisfaction acknowledgement. When the session is over, the router uses the last collected acknowledgement to withdraw funds from the smart contract. Finally, the client is automatically refunded for all unused satisfaction acknowledgements. Now let's take a closer look at the HANSA protocol. The HANSA protocol is established between the client and the router. The protocol includes 2 major sessions, the handshake session and the main HANSA session. The connection session begins with the client sending the router a connection request. If the router is ready for service, it replies with a greeting. Then the client generates a secret hash chain and sends it to the router along with other data. Next, the router prepares the smart contract, which is pre-deployed, and sends the client its address. The client verifies the bytecode of the smart contract and the price hard-coded in it. If verification fails, for example, due to an unexpectedly high price, the handshake fails. Otherwise, the client funds the smart contract and notifies the router about the payment. The router checks the payment and activates an unrestricted permanent internet access. This is when the main HANSA session begins. The main HANSA session includes timer-activated periodic satisfaction acknowledgements sent by the client to the router in the form of session hash chain hashes. The router verifies that the hash indeed is the next link of the hash chain and extends the internet access for another small period. This satisfaction acknowledgement cycle continues until the client disconnects or the session expires. It is important to note that if the next acknowledgement misses the deadline, the session pauses and can be resumed any time until certain deadline. Now let us see how DAPSET helps client to decide whether to send next satisfaction acknowledgement or not. DAPSET is a low overhead bandwidth estimation technique that allows to establish the dependency between the payment and the quality of service. The smart Wi-Fi client can specify in the settings the minimal desired available bandwidth. During the main handset session, the client performs periodic low overhead probes by downloading payloads of different sizes from a set of dubset servers scattered across the globe. Then the client estimates the speed of each probe and filters out unreliable probes using the effective payload function. It calculates the speed of the transmission component through dividing the payload differences by the difference between retrieval delays. This way, dubset excludes the propagation, processing, and queuing delays from the readings. Now, the analysis of the readings from dubset servers allows the client to estimate the available bandwidth delivered by the router. As a result, the client can automatically estimate the quality of the internet connection and make decision whether to provide the next satisfaction acknowledgement or not. This arrangement creates a direct dependency between the quality of service and the payment. Dubset probes are very small, about 10 kilobytes, which creates a negligible overhead and therefore allows to perform frequent probes. To summarize what I've just said, smart Wi-Fi includes three types of system components: smart contract, router, and client. Hence, the protocol ensures trustless and fair communication between the client and the router. Also, the dubset technique allows to automatically estimate the quality of service using low overhead probe. Now, let us step into the smart Wi-Fi implementation. We implemented the entire smart Wi-Fi system, which includes three components: the smart Wi-Fi wireless router, the Android client, and the Ethereum smart contract. The implementation of the system includes 1,858 lines of code, and the entire system is open source and published on GitHub. We implemented the router using Java programming language and Raspberry Pi connected to a Netgear MIMO router. This configuration allows to avoid modifying the manufacturer's firmware on the Netgear router. For the client portion of smart Wi-Fi, we implemented an Android app. This is important to note that smart Wi-Fi does not require rooting or jailbreaking of the smartphone. We implemented the smart Wi-Fi smart contract using the Solidity programming language. We used Rapston and mainnet networks for deployment and testing. You can also interact with the test deployment of the smart contract on the Rapston Etherscan. We performed a thorough evaluation of our prototype to demonstrate that the system is ready for production use. We measured all the essential parameters of the system, including delays, fees, smart contract storage use, systems communication overhead, and scalability of smart Wi-Fi. One of the challenges of blockchain-based systems is notoriously slow execution. In smart Wi-Fi, however, we leverage off-chain execution, grace period, and parallel tasks to eliminate long delays. The delays in smart Wi-Fi are subdivided into three groups. First group is connection initiation. The second group includes handshake verification and funding. The third group comprises payment and refund. Based on 10 probes, we measure average delays in seconds with recommended gas price settings. To demonstrate the independence of delays from blockchain hash power, we perform measurements in low-powered Rapston testnet and heavy-powered Ethereum mainnet, showing that delays in both networks are similar. As we can see from the table, the clients enjoy internet connection after only about 4 seconds, while the remaining delays pertain to blockchain processes which do not interfere with the end-user experience. The Ethereum transaction fees are measured in the unit named gas. We measured the fee overhead for each of the 9 types of smart contract transactions. Then we convert the gas cost into the United States dollars. The read-only transactions do not incur any fees. The blockchain appending transactions require paying fees, since smart Wi-Fi uses an off-chain execution protocol with infrequent smart contract transactions. The resulting fee overhead is much lower than, for example, credit card transactions. Although the cryptocurrency price fluctuates, the fees amount in dollars stay approximately the same due to the gas price and gas limit mechanisms in Ethereum blockchain. Ethereum smart contracts allow very limited data storage. The table juxtaposes the smart contract storage used in smart Wi-Fi with hypothetical storage without hash chain compression. The smart Wi-Fi design uses hash chains for satisfaction acknowledgements, which means that it is sufficient to store only one hash value per session. Without the hash chain design, the storage of every acknowledgement would have incurred very high delays and fees. As we can see, smart Wi-Fi only stores 116 bytes per 1 hour session. Next, we show the 60-minute session communication overhead for different smart Wi-Fi calls over 10 measurements. The low communication between the client and the router involves only a few kilobytes per session. It's local communication. Although the blockchain API communication, which is not remote, exchanges more data, it is still less than 1 megabyte per hour. A smart Wi-Fi router can accommodate many simultaneous clients. We connected multiple client processes to our smart Wi-Fi hotspot and simulated active web surfing traffic, with the results shown in this figure. The vertical axis shows the maximum number of simultaneous clients that the router could serve. The horizontal axis shows the dubset limit set by all the clients. For example, if the router connected to a 100 megabit per second Ethernet link and the clients are satisfied with a 4 megabit per second speed, the system is capable of serving about 150 simultaneous web surfers. To summarize our presentation, smart Wi-Fi leverages the power of smart contracts to protect clients from non-service and hotspots from non-payment, all at the same time. It allows to automatically control the quality of service and therefore create an incentive for providers to deliver higher speed and reliability. With smart Wi-Fi, we envision a fully automated cross-domain authentication between wireless access points, forming a global permissionless decentralized network of free and paid Wi-Fi hotspots. Smart Wi-Fi automates authentication and payment to allow clients to connect to new hotspots without manual interaction. The entire implementation of smart Wi-Fi is open source, and we invite everyone to use our code for evaluation, collaboration, and building your own products. Thank you very much for attending our presentation, and we are ready to answer your questions.
Hello, ladies and gentlemen. I hope you are doing well. It's an excellent opportunity to present our research work to you. My presentation topic is EW256-357, a new secure NIST P256 compatible elliptic curve for VoIP applications security. I am Nilanjan Sen, one of the authors of this paper. My co-authors are Dr. Ram Dantu and Dr. Kirill Morozov. This is the outline of my presentation. First, I'll give a short introduction to the topic. Then I'll discuss the elliptic curves, the elliptic curve cryptography, and the motivation of our work in brief. In this work, we have developed an elliptic curve which can be used for VoIP or voice over IP application security, such as real-time audio and video security. I'll discuss the security traits of our proposed curve in detail. Next, I'll discuss the experimental setup used to test our proposed curve, its performance analysis, followed by the conclusion. Elliptic curve cryptography is a well-known asymmetric key encryption scheme proposed by Victor Miller and Neil Koblitz. It has become popular in the field of the cryptography since the last decade. It is a lightweight encryption scheme because its key size is smaller than other asymmetric key encryption schemes such as RSA. Its computational time is less than the other asymmetric key schemes as well. Many elliptic curves are developed so far, and some of them are commercially used in the security field. The most popular curves among them are the NIST curves or NIST curves. That means they're recommended by the National Institute of Standards and Technology of USA. However, some researchers are skeptical about the NIST curve security because they think those curves are vulnerable to certain attacks. In this work, we have developed a new 256-bit elliptic curve which is compatible and more secure than the popular NIST P256 curve. The word compatible here signifies that our proposed curve is compatible with the applications which support the NIST P256 curve. Finally, our proposed curve is suitable for voice over IP applications security as well. Now I'll give a short description about the elliptic curves, its properties, and the elliptic curve cryptography. Elliptic curve E over a field K can be represented by three forms or three equations. First one is the well-known Weierstrass form, that is y square plus axy plus by is equal to x cube plus cx square plus dx plus e. There is another form of it, that is the short Weierstrass form that we have used in our present work. Apart from Weierstrass form, there are other two forms also, that is Edward form and Montgomery form. Now the keyword elliptic curve, it has no relation with the geometrical figure ellipse. It is named because the Weierstrass equation is similar to the equation used to calculate the circumference of an ellipse. That's why the name elliptic curve. Here you can see two examples of the elliptic curve of two given equations. You can see the equations below the figures. Now, elliptic curve has two basic operations. One is the points addition, another is point doubling. Point addition states that if P and Q are 2 points over an elliptic curve E, then if we add these 2 points, then the result will be another point R, where that point R is also a point over the elliptic curve E. Next, the point doubling states that it is the addition of the same point. So if we choose a point P over an elliptic curve E, then P plus P will yield 2 times P. Apart from points addition and point doubling, we have another very important operation of elliptic curve, that is scalar point multiplication. And this means first we will choose one elliptic curve point P, and we will multiply that by a scalar value n. So n times p is equal to p plus p up to total n minus 1 number of additions of the same point p. Now the scalar point multiplication is very important in elliptic curve cryptography as well, because using this scalar point multiplication we do different ECC operations like the key generation or the encryption and decryption operation. Now elliptic curve cryptography uses elliptic curves, and usually two types of elliptic curves are used. One is the prime curve over the GFP, where p is the prime number. Another is the binary curve over GF2 to the power m, where m is a positive integer and each element of the field is m bit long. Now in our present work we have used the prime curve over GFP. Now I told that we have used the short Weierstrass form to develop our curve, and the short Weierstrass form is y square is equal to x cube plus ax plus b whole modulus of p, where p is a prime number and p must be greater than 3. Now elliptic curve cryptography has a very important property, that is the elliptic curve discrete logarithm problem. So this problem is actually believed to be unsolvable, and we use this ECDLP to generate the elliptic curve public and private key. So this problem states that if we choose 2 points P and Q over an elliptic curve E, then it is extremely hard to find the value of R, where R is some variables, basically a scalar variable, from the equation Q is equal to R times P. Now this equation is used to generate the public and private key, where P and Q are known to everybody. R is treated as the private key and Q is treated as the public key. So these are the basic concepts of elliptic curve and elliptic curve cryptography. Now elliptic curve cryptography is better than RSA. We discussed that in the first slide, because the key size of the ECC is less than the RSA. Here in this table we can see that to achieve the 80-bit security level of the security, RSA requires 1024 bits of key size, where ECC needs just 160 bits of key size. For 256 bit of security, RSA needs 15,360 bits of key size, where ECC needs just 512. So definitely ECC is better than RSA in this context. Now, among the other elliptic curves, we know that NIST P256 curve is the most popular one, but it has some weaknesses, because the researchers, some of the researchers have doubts that there are probable presence of some backdoor in the pseudo-random generators used in the NIST elliptic curve generation process. Now these pseudo-random generators are very essential thing that is used to generate the NIST elliptic curves, and researchers have doubted that there are some flaws, some drawbacks which makes these NIST elliptic curves vulnerable. Secondly, NIST curve generation is not fully transparent. Usually when we develop any elliptic curve, that elliptic curve contains multiple parameters, and the parameter generation process must be transparent to make the elliptic curve a secure one and trustable one. But some of the parameters of the NIST curve is not, the generation process of those parameters are not fully transparent. Thirdly, researcher Bernstein and Lange has claimed that NIST's ECC standards create unnecessary complexity in the ECC implementation. And finally, NIST curves are not twist secure. This twist security is very important in elliptic curve cryptography. We will discuss in detail what is the twist security. So if a curve is not a twist secure curve, then these curves will become the vulnerable to some attacks. Next, we're coming to our proposed curve. So we have used the short Weierstrass curve of this form, and the parameters of our curve are basically 6 parameters, which are represented in a 6-tuple notation, where P, the first one, is the prime number, which is very important and is required to generate any elliptic curve. Second one, R, is the order of the curve. So order of the curve means the total number of points present on the curve. Now, to make an elliptic curve secure, that order of the curve R must be prime. Then we have A, the first coefficient, and this is -3. Usually in short Weierstrass curve, NIST also follow that the value of A is -3. The second curve coefficient is B. We have generated it separately. Then we have the base point G, which is nothing but the x and y coordinate. Each elliptic curve has a base point with x and y coordinate, and those points are represented as gx and gy. And finally, we have a cofactor represented as h, and usually for each prime curve, the value of cofactor is 1. So these are the 6 parameters of the elliptic curves, and based on this, we have generated our elliptic curve. First, we have chosen those parameters, and then based on those parameters, we have developed the elliptic curve. And in the next slide, you can see our elliptic curve's equation is y square is equal to x cube minus 3x plus 5029, where a is -3, b is 5029, the second coefficient, and the name of our curve is EW256357. So basically, E stands for elliptic curve, W stands for Weierstrass, because we have used short Weierstrass equation, and 256357 represents the prime number that we have chosen. So basically, this is, we have chosen the prime number, that is 2 to the power 256 minus 357. So below you can see the values of the 6 parameters. Here the P is the prime number that we have used to develop this curve, and the value of prime number is given here, which is nothing but 2 to the power 256 minus 357. Then this is the value of the R, that is the order of the curve, and this is prime as well. Value of A, the first coefficient is -3, the second coefficient is 5029. Then we have the base point G with the two coordinates x and y, where gx is 1 and gy is a large number here, and the cofactor h is 1. So these are the parameters. In our paper, we have described in detail that how all those parameters have been chosen. Now we will come to the security features supported by Weierstrass curve. Basically, there are two categories of the security. One is the ECDLP security, another is the ECC security. So Weierstrass curves supports the 5 securities. So since our curve is a Weierstrass curve, so we will discuss those 5 securities only. So first one is the row complexity, which is calculated as 0.886 times root over R, where R is the order of the curve. And if the order of the curve is small, then the ECDLP can be broken. But we have just shown that our R, the value of R, this order of the curve is very large, and it is prime as well. Then we have the transfer. Transfer is a method where ECDLP can be converted to the linear algebraic group discrete logarithm problem. So if ECDLP can be converted to this, then ECDLP can be broken. So there are two types of transfer, that is additive transfer and multiplicative transfer, where additive transfer is used for the smart ass attack, means it is vulnerable to smart ass attack, and multiplicative transfer, it is vulnerable to the MOV attack, or manages Okamoto-Vanstone attack. Then we have the complex multiplication field discriminants D. The elliptic curves D must be greater than 2 to the power 100. If that elliptic curve is secure, then it must be greater than 2 to the power 100. And in our curve also, we have checked that the value of D for our curve is much greater than 2 to the power 100. Then we have the rigidity, that is, everything should be generated in a transparent manner. It should not be any there should not be any manipulative process to generate all the parameters. So that is known as the rigidity. And finally, we have the twist security, that is required to prevent some well-known attack, for example, the invalid curve attack. So a curve is a twist secure if its corresponding twist secure curve is x cube plus ax minus b, and order of both the curves are prime. So if our curve is y square is equal to x cube plus ax plus b, then there must be another twist curve, that is y square is equal to x cube plus ax minus b, and order should be prime. So based on this, you can see a comparison of the row complexity, transfer, CM field discriminant, rigidity, and the twist security. So our curve is fully rigid, but NIST P256 in some parameters it is manipulative. Our curve is strongly secured, and it is NIST is weakly secured. Then for discriminant and the row complexity and transfer, our curve is secure. From this table, we can see that. Now let us come to the experimental setup. We have done experiment to check whether our curve is suitable for voice over IP application security or not. So this is the experimental setup, the server configuration and client configuration. So for the performance analysis, we have used two parameters. One is the end-to-end delay in milliseconds, another is jitter in milliseconds. Now jitter means the delay variation. From the figure you can see here. So this sender is transmitting the packet in some particular time interval, but here the time interval, there is a huge gap in this time interval when the receiver is receiving it. So this is known as jitter. So in case of voice or video transmission, if the jitter is high, then there will be some problem. So encryption and decryption time in our experiment is measured in milliseconds. So this is the comparative analysis of different ECC applications. So we have the point addition, the point doubling, scalar multiplication, and another type of scalar multiplication which is faster than the normal multiplication, that is fixed window based scalar multiplication. You can see here that our curve is performed better than NIST curve, P256 curve. And we have some other two operations also, that is the elliptic curve Diffie-Hellman key exchange, and this is ECDS, the digital signature algorithm. So for these two operations also, our curve performed better than NIST curve. Though the difference is not much, but still it is performed better. Now let us come to the comparison between the two curves in terms of the delay and the jitter in audio and video. We can see that the end-to-end delay means the receiver is receiving and sender is sending and receiver is receiving. So this end-to-end delay comparison, NIST's delay is little less than our curve, but that is 0.07 millisecond, which is negligible. For the video encryption also, it is very negligible, that is only 1.25 millisecond. For the jitter curves, we have seen that the jitter for the audio encryption and the jitter for the video encryption, in both the cases, our curve's jitter is less than the NIST curves, though the values are negligible. So we can see that in these four curve plots, we can see that our curve's performance is on a par to the NIST curve's performance. And basically, our curves, the main goal of this work is to generate a secure curve than the NIST P256 curve. So in the conclusion, we can say that our proposed curve is compatible with NIST P256 curve. Its execution time is faster in terms of basic operations. Curve provides 128-bit security. It's more secure than NIST curve. The delay and jitter difference is very negligible here, so we can say the performance is on a par, and the curve is suitable for real-time media encryption as well. So our curve can be used in the VoIP application security. So this is the presentation of our work. Thank you very much for listening the presentation. So if you have any question, you can ask me.
Hello, everyone. I'm honored to make this presentation to share recent works at this conference. My name is Jiahui Zhang. I am a master's student from Ocean University of China and am currently researching wireless network security. Today, my topic is PEDR, a normal evolution attack detection scheme based on phase error drift rate. My presentation will include these 6 parts. In section 1, I will introduce the background of our research. In section 2, I will give the attack model and the problem that our scheme solves. The related work and the motivation will be shown in section 3, and then I want to introduce the solution PEDR, which is a normal ET detection scheme. In section 5, we will show the performance evaluation, and finally, I will make a conclusion. Well, let's move on the first part of this talk. In recent years, wireless networks have developed rapidly. Compared with wired networks, WLAN has the advantages of flexibility, mobility, and expandability. Now I will use a figure to briefly introduce the basic structure of WLAN. The wireless access point, referred to as AP, connects to the Internet via Ethernet and receives wireless signals. The user mobile device, such as mobile phones and laptops, receive signals to connect to the AP and transmitted data to the Internet. Obviously, AP is the key to WLAN. Because of this, AP has become target of attackers. AP faces many security threats, such as wall driving, man-in-the-middle attacks, and rogue AP attacks. These attacks can leak user privacy and sensitive information, and can even cause direct economic losses to the victim. For example, Albert glides in the United States drive a car to search for and attacked insecure WLANs, and 41 million credit card numbers were stolen and sold. In 2015 years, the economic loss of online banking and account theft caused by insecure WLAN in China amounted to more than 5 billion yuan. Billboard damage is just the tip of the iceberg. To prevent wireless users from being attacked, the policy purpose is to detect these attacks. Secondly, I would like to introduce the attack model and the problem in our paper. This time, we will focus on rogue AP attacks. You could also call it evolution. I'm going to introduce you to how it attacks. The attacker first pretends to be a legitimate AP by cloning the SSID of it and other related parameters. You can see that the two APs in the figures have the same SSID. Yes, it's free Wi-Fi. Then the attacker performs a denial of service attack on the legitimate AP. That's a step 1 in the figure. Or provide a stronger signal than a legitimate AP to induce wireless users to connect with it. Once a victim is connected to the ET, the user information will be sent to the attacker through ET, which is the process 2 and 3 in the figure. The attacker will steal the victim's sensitive information or launch further attacks. So, when we want to connect to an AP, how do we judge whether it is a legitimate AP? To solve this problem, researchers have proposed many methods. Among them, Liu et al. Proposed a CSI-based detection scheme. This paper was published at the InfoComm conference in 2019 years. Before introducing this method, please allow me to briefly introduce CSI for everyone. Channel state information, we call it CSI, is the channel attribute of wireless communication links. It includes the combined effects of scattering, fading, multipath, and power decay on the signal propagation path from transmitter to receivers. Besides, CSI consists of amplitude and phase information of each subcarrier. Liu et al. Filtered and normalized the collected phase information and extracted the phase errors from it. Nonlinear phase errors are used as a fingerprint to uniquely identify the device. In order to reconstruct the method of Liu et al., we set up the same experimental environment and conduct experiments. The exact experimental result is shown on the left. That is, the phase error obtained in a collection. Unfortunately, from the reproduction experiment results, we can observe that the nonlinear phase error is unstable and drift. In the figure, it can be clearly observed that some of phase errors overlap each other. We believe that the device with similar fingerprints can't be effectively identified due to overlap caused by drift. In order to verify the universality of the overlapping phenomena caused by the phase error drift, we expanded the scale of the experiment and found more similar phenomena. Therefore, we believe that attackers can use this phenomena that overlaps caused by drift to deceive detection. If an attacker deliberately chooses a device with a fingerprint similar to a legitimate AP, this method will generate a lot of false negatives, which will lead to a failure of detection. At the same time, we found that the drift of this phase error is regular, and phase error of each device drifts within a unique range. Therefore, we consider that using the drift rate of phase errors as the fingerprint will achieve higher accuracy detection. And based on this, a new detection scheme was proposed. Okay, now we move to the part of this solution. Here you can see a figure that shows the overview of our solution. PEDR uses the drift range of the phase errors as the fingerprint. It can be divided into two parts: the fingerprint library establishment and legitimacy detection. PEDR first collects the fingerprints of legitimate device to establish a fingerprint database. Before connecting to the target AP, it collects fingerprints for comparative testing to determine the target AP's legitimacy. The entire process doesn't require additional hardware equipment and protocol modification. Now I'm going to introduce the first phase of PEDR. This model is responsible for establishing a legitimate fingerprint library. The fingerprint library is composed of a large number of legitimate AP fingerprints. There are three main points in the composition of fingerprints, namely the fitting technology, the fitting function of drift range, and distribution area S. For each experimental device, in order to make a fingerprint based on phase error drift range, the maximum range of phase error drift must be obtained. Therefore, the detection terminal needs to collect a sufficient amount of CSI data and establish the phase error from it. The bound functions Fmax, Fmin of the drift range are obtained by fitting extrema of phase error on each subcarrier with the cubic function. PEDR uses the functions obtained by the fitting technology to represent the drift range of phase error, which is more intuitive. In addition, the phase error distribution area S on the phase error graph is determined by the defined intergraph method. The fitting functions Fmax, Fmin, and the distribution area S are stored in the dictionary FPI as the device fingerprint. Then, phase 2, legitimacy detection is the most important part of PEDR. Through three parameters, the number of intersections of upper and lower bounds, and the 0-point difference value, and the distribute area, PEDR can determine the target fingerprint's legitimacy. First, we need to collect the fingerprint of the target device. The legitimate fingerprint FPI is extracted extracted from the legitimate fingerprint library according to the SSID and MAC address of the target AP. The detection process can be divided into 3 stages. In the first stage, the number of intersections is used to determine whether the target device fingerprint and the legitimate fingerprint are crossed. Some phase errors or subkeys 28 and -28 are both zero. There are at least 2 intersections between the boundary sections. Therefore, if there is a third intersection between upper boundary and lower boundary in the range of subkernel -28 to 28, it means that the boundary in the fingerprints across each other, and 2 fingerprints are clearly different. As shown in Figure 1, the target AP is considered an ET. Otherwise, it means that the target AP fingerprint and the legitimate fingerprint are separated, contained, and partly overlapped, as shown in Figure 2, 3, 4, and 5. We define the difference between the 0-point value of the legitimate AP and the target AP as the 0-point difference and use it for further judgment. In the second stage, we observe the positive and the negative attributes of the product of the 0-point difference to determine the relationship between the 2 fingerprints. If it is determined that then the target fingerprint is separated from the legitimate fingerprint, or the 2 partly overlap, or the target fingerprint contains a legitimate fingerprint, then the target device is determined to be an illegal device. If the legitimate fingerprint contains the target fingerprint, there may be some difference in the fingerprint distribution range, as shown in Figure 3 and 6. Therefore, the phase error distribution area is used to distinguish 2 devices. At this moment, the threshold TSV is introduced. If the absolute value of the difference between 2 is less than TSV, PEDR considers that the 2 fingerprints are coincident and the target AP is legitimate. Otherwise, the fingerprints are considered included, and the target AP is determined to be an ET. Next, we evaluated the performance of PEDR in a simulation scenario. The table shows the specific types and quantities of device. The validity of fingerprints based on the phase error drift range can be more scientifically explained by using different types of device as target APs. At the same time, we use multiple devices of the same model to clarify that the fingerprints of devices of the same model are also different, which means that attackers cannot using devices of the same model to circumvent PEDR. Our simulation experiments are carried out in laboratory, which is a typical office environment with the size of 11 meters x 6 meters, and contains desks and other furniture, as shown in the figure on the right. The position of the serial number 1 to 9 is used to place the target equipment, and the detection equipment is placed in the position 0. Obviously, the target device in the different positions can provide different CSI information, which is more helpful to verify the validity of the fingerprint. We conduct a performance evaluation of PEDR. Experiment results shows that compared with Liu's method, PEDR had advantages in equipment detection rate and false negative rate, due to the existence of devices with similar phase errors in the experiment. The phase errors of this device have overlapped each other due to phase error drift phenomena. This method based on phase error is difficult to distinguish such target device. It is easy to generate false negative results. Therefore, the false negative rate of this method is as high as 15.56%. In comparison, The attack detection rate is only maintained at about 84.44%. The detection rate of PEDR is still stable and as high as 98.89%, and only a few keys have a false negative rate of 1.11%. Finally, I will make a summary of our work. In this work, we have made 3 contributions. First, we innovatively proposed the fingerprint based on the fixed error drift ridge for ETA detection. Secondly, compared with existing detection methods, PEDR doesn't require additional hardware equipment or protocol modification. Last, PEDR has a unique detection algorithm to complement ETA detection, especially in the sense of equipment with similar phase errors. That's all my presentation. Thank you. If you have any questions, please feel free to contact me. Here is my email address.
Hi everyone, I am Yuang Rong. I'll go with Peter. Today I'll be sharing with you our recent work, Integrity, finding integer errors by targeted fuzzing. Now this is a joint work between UC Davis and Python's AI Lab. So let's dive in. A little bit background first. We all know integer errors, but what we don't know is how severe it is. Now integer errors can cost a lot. For example, in 2018, hackers created massive amounts of beauty coins in 2 transactions using an unsigned integer overflow. And there are more and more similar cases. The number of integer-related CVEs reported from 2016 to 2018 rampant from 104 to 635. What we're trying to do is to find integer errors, and our solution is targeted fuzzing. So let's dive into our design. Our design is two-folded. First, exploitation, then exploration. Exploitation is statically instrument instructions to exploit potential integer errors. As we know, most of the integer errors go unseen, as most of the people don't notice them until they cause damage. So we instrumented the binary code so that every time there is an integer error, we will raise a flag and tell, hey, an integer error just happened. Now, for exploration, we will dynamically target each branch to fuzz and find a proof of concept that says, hey, this integer error is real and it's possible to happen. Here's an example input that triggers this integer error. Now, going forward, I'll be using the following example code to show what we're going to do on the source code. Now, it's a relatively easy one. Now, you have 2 unsigned values. You do something to it. You either add or divide. The result is used later. This program has 5 basic blocks, and the control flow graph is drawn to the right. For exploitation, every time we find a integer operation, we will try to promote each operand to a higher precision, because the same operation will not overflow in a higher precision one. Then we try to infer the bit width and the sign of each operand to determine the upper bound and lower bound of the operation. We will test that in a higher precision if the result is higher than the upper bound or lower than the lower bound. Here we instrument a guard branch to do that, and when it's tested for true, we will report an overflow. There are some special designs for divide, because you don't need to promote divide to a higher precision to know if it is a divide by 0. You just test the divisor, and that's it. There are some special optimizations we've done here. For example, 2 unsigned values, when added together, they cannot underflow. And there are a full list of possible optimizations that we put, and it's discussed in detail in the paper. But overall, we reduced 10% of our all guard branches. So going forward to exploration, at compile time, we have already labeled 2 different branches. One is guard branch, which is we inserted to test if integer error is possible. Here we labeled them as blue. And another one is original branch, the branches that are originally there. Here we tagged it as red. We will collect all the branches and sort them in a priority queue. We give each branch an initial priority. And the special design here is that we guarantee that original branch always has a higher initial priority. The rationality is that we believe original branch is easier to solve compared to guard branch, as guard branch represents a integer error, and integer errors should not be seen often in a program. Now, integrity, we will try to solve a branch on top of the queue every time. It either successful or it fails. If it's a success, either we found a new seed, and so we can keep doing keep fuzzing, or it's a proof of concept that certain integer errors just happened. If it fails, we will put it back to the queue and try to solve it later. Another special design here is that we don't stop fuzzing even when an error appeared. Now, unlike memory errors where your program halts immediately when a memory error happens, integer errors will not halt your program. So we will try to continue the execution and see the overflowed value will cause any later damage to the program. Later, I'll share you with the case where an overflowed value, seemingly benign when it happened, caused a crash later. I know that some of you may be asking, so what's the difference compared with UBSync? So we done an experiment compared with the state-of-art fuzzer Angora and UBSync. We actually find 151 more errors on popular open source libraries compared with Angora. The reason that is UBSync may tell you that there is an integer error when it happens, but it cannot do direct fuzzing and cannot tell Angora, hey, there is a potential error, so try to fuzz it. UBSync doesn't do that, and Integrity does. A more interesting thing is to take down all the errors that Integrity found. And here we have 4 divide by 0 crashes, that's trivial. We have 4 overflow to crashes. One of them is the variable is used to allocate a certain amount of memory, and that value overflowed to a huge amount. So when trying to malloc a huge amount of memory, it crashes. Now, what's more interesting is the last 2 columns, harmful and benign ones. So what's harmful and what's benign? We believe benign errors are those who is an error but did not cause the program to misbehave. And harmful ones are those who triggered unexpected behavior, for example, to produce a wrong result. Now, first I want to say is that benign errors is not false positive, it's still an error. And after some investigation, we find there are 2 main reasons why these errors exist. First, it's generated by compiler. Now, compiler sees everything and has a piece in mind that even though this operation may overflow, when it overflows, it's never used. So it does it anyway for the sake of optimization. There is a case in our paper that discusses how this happened in detail. And another one, which is more common, is intentional. The programmers intentionally write it for their own convenience or other purpose. For example, if you want to take the last few bits of a variable, what you might write is probably like v left shift by amount, right shift by the same amount. But when you're left shifting, it's possible that you have an overflow. And what's more, when v is a signed value, left shifting cause overflow is actually an undefined behavior in C standard. And we find that often. So how do we separate them? In the previous table, we did that all manually. We inspected every error and tried to tell if this is harmful or not. And it's quite tiresome, if you ask me. So how do we do the job automatically? Let's go back to the control flow graph that we had earlier. And let's say we have these 2 different traces, and both of them stacked into 6, which represents a unsigned overflow. What's wrong about it? It contradicts with our assumption. It feels that harmful errors in popular open source programs are rare, because if it can be easily found, it's most likely being reported and fixed way earlier than we do. And we also assume that graph branches should be hard to solve. So how can this branch be solved so easily at an early stage? So using these heuristics, we actually does the statistics of place method to tell benign errors from harmful ones. So for each error, we see how often it occurs in all traces. If it appears too often, it's most likely benign. And the threshold we use here is 95%. That is, of 95% of all traces, you have the same error, then most likely it's not an error. So using this method and the ground truth by our manual inspection, we have almost 80% of precision and 37% of recall. So we efficiently rule out part of benign errors and reduce the human labor. I'm not saying it's totally automatic. You still have to manually inspect it at the end of the day, but you have a helper. So another way is to compare independent implementations. So if you have the same algorithm, which is deterministic, and you have different implementations, then giving the same input, you should have the same output. So here we tested on LabJPEG IgG and LabJPEG Turbo. We first LabJPEG IgG and found a huge amount of integer errors. LabJPEG Turbo is a optimized version of LabJPEG using SSE instructions to accelerate the calculation. So we calculate L1 distance of the same file decoded by two libraries. The L1 distance is defined as the following. So for each pixel that is different, on average, how different is that pixel? What's the L1 distance of the different pixel? So we drew the CDF here, and for normal images, is the images we randomly found from test images online, and the average difference is less than 10. That means it's for each different pixel, the difference in 3-channel combined is less than 10. That's barely human-eye recognizable difference. But for exploit images, that is the images we internally generated and has a error in it, the difference can ramp from tens to hundreds. Here, we have certain example of what it looks like. Now, internally generated exploit image and decoded by two library. Here are two images. Here are the file we selected, and you can find L1 distance is like 200, where you can see the image is different when decoded by two library. A more striking example here we have is the difference is 342. But keep in mind that the maximum possible value for L1 distance is 255 times 3, because you only have three channels, and for each channel, the maximum difference is 255. So this is pretty striking when we found this. Now, in conclusion, integrity does targeted fuzzing to trigger integer errors. And when we're doing evaluation, we found 174 integer errors, of which 8 are fatal crashing errors, and we found 151, more than the state of our father. Now, using stacking trace and different implementations of the same algorithm can help us separate benign errors from harmful ones. But in the end of the day, you still need human interaction to determine. So fully automated separation are hard, and it remains an open question for our work. And that's everything. And thank you. Any questions?
welcome to this presentation on selecting privacy-enhancing technologies for IoT-based services. My name is Immanuel Kunz, and I wrote this paper together with my colleagues Christian Banse and Philipp Stefano. We are researchers at Fraunhofer ISAC, which is a research institute for IT security in Munich, Germany. So let me start with a few thoughts on the motivation for this work, which was basically that selecting privacy-enhancing technologies, PETs, is difficult. So given a set of data, given a set of privacy requirements, privacy goals, it is difficult to match these technologies appropriately with the data you want to anonymize. There are some works that usually focus on risk-driven methods. Like, for example, Linton assumes that you have a system design and a data flow diagram where you can identify potential privacy threats in the data flows, and it will then suggest you a rather unspecific, a rather large list of privacy-enhancing technologies to mitigate these risks. But like I said, these lists are rather unspecific. So what we came up with was a list of criteria, and these are data-driven and service-driven criteria, which can be used to evaluate the applicability of certain PETs or categories of PETs for data types or kinds of data. So I will first go into a bit more background into what kinds of PETs we actually consider for our approach. We call these data-dependent PETs. And then I will go into these criteria I just mentioned, which we embedded in a general process for the selection of PETs in IoT-based services. And after that, I will also go through an example application and discuss some goals we had in mind for this process. So first of all, the PETs that we considered are such technologies that manipulate data in some way. That is why we call them data dependent, because they take some kind of data as an input and only will accept certain kinds of data as an input, manipulate this data somehow, and output a somewhat anonymized data. We categorize these into deterministic distortion and randomized distortion techniques. For example, recoding would be such a deterministic distortion technique where for example, a numerical value is rounded or masked, or a categorical value is generalized. So these work in a deterministic way as they are parameterized. And the randomized distortion techniques manipulate data in a randomized way by, for example, adding a randomized value or swapping values around. Okay, with this, I will go into the process design now. And the scenario we consider for this process is a service that collects data from a number of IoT devices and uses this data, analyzes it, uses it to provide this service. So later I will show you an example of an usage-based insurance service that collects data from a number of automobiles about their speeds and so on to calculate a risk factor about the driving behavior of the drivers. This is the kind of service you can keep in mind for this process. And the first step of the process would be a service description, first of all. So in this step, the service provider defines the purpose of the service, defines the actors, who is the data collector, who is the data subject from which data is collected, and define the data that is really required in order to fulfill this purpose. So this description then goes into as an input to the second step, which is the data-driven elicitation. So this takes the service description and the categories of PETs that I showed you earlier and matches the PETs with the required data to output a set of technically applicable PETs. And the way this works is all these criteria here are evaluated against the required data. So for example, we have here continuous and categorical data. This is probably the simplest criterion here, which concerns simply the input type of the PET. So some PETs can only process categorical or continuous data, and thus certain PETs can be ruled out here according to the type of the input data. Also, the set size of the data influences the applicability of PETs. The property of the data of being ordinal or nominal, so if it can be ranked in a way, influences this applicability, the data's longevity. Another example is the value sequentiality, which limits the applicability of randomized distortion techniques. So if you stay in this automotive example, where a system in the automobile generates data in a known sequence, then distorting one of these values in a randomized fashion does not necessarily lead to a good anonymization, because the service provider might still be able to infer the original value if this sequence of values is known. And lastly, there are metadata and identifiers, which of course can lead or which cannot simply be distorted randomly, because they would, for example, identify another device then. And the output of this step would then be a set of technically applicable PETs, which, however, do not yet help us in making a statement about if they are really meaningfully applicable, if they are really usable for the service. For that, we also have to consider the criteria that the service itself has towards the data. And we identified these three criteria here for the service-driven criteria. So value precision is the first one here, and regards the granularity that the service requires from the data. For example, for continuous data, this could be the decimal place that is required. And as such, it gives the service provider also an idea of how to parameterize the PET later. Data freshness concerns the question of how fast the data is required. So if it's required, for example, in near real time, certain PETs might not be usable because they introduce too much latency into the data transmission. And finally, there might be attribute dependencies, where if a certain data is manipulated using one PET, another one needs to be processed using the same PET, because the service might need to infer statistics about these data, like correlations between the data. So they have to be manipulated at least in the same way. And this step then gives us a set of really usable PETs, meaningfully applicable PETs for the set of required data. And this goes into the last step, the actual PET selection, where the service provider can select PETs from the set. And we didn't go into all the details here in the paper, but gave an overview of what could be the criteria again, which a service provider might consider to when selecting PETs now. So one could be implementation cost, the complexity of its implementation, or the service provider might also target certain privacy metrics or have internal compliance requirements that influence this decision. But it could also be possible that this set of usable PETs is actually empty. Of course, that's a possibility. And in this case, it may be possible that the service provider obtains the consent or additional consent to collect this data, or that the service is simply not implementable. So I will go into the example application now. So what we did here was we did not just go through one use case for this process, but we first of all, we mapped our criteria to a data taxonomy for automobiles. So what we did was we categorized data that is generated by automobiles according to the data-driven criteria I showed you in step 2. And this is the taxonomy we came up with. So you can see here there's, for example, stream data. This is data that is continuously generated by sensors. There's state variables which follow this criterion of value sequentiality, like I explained earlier. So we built this taxonomy and put it into this table to see which PET classes are applicable or not applicable, or are applicable in a limited way to these categories, to make this second step of the process really easy to apply for any automotive use case. So now I will go through this example of the usage-based insurance that I mentioned earlier. So we imagine that this service requires two kinds of data, which is the vehicle speeds and the state of the assistance system of the adaptive cruise control, the ACC state, which could be following another vehicle or accelerating or simply switched off. So because this is considered a safety feature by the service. The second step would then be selecting PETs or eliciting PETs according to this table we saw before. So I will go back here quickly. And we can easily map this kind of data to the categories here, with speed data being stream data. And we can see that most of the PETs are applicable here. And the ACC state is a state variable where we only can apply recoding without limits. This goes into the third step then. Here we could imagine that this service requires the data, has certain precision requirements towards the data, like that the speed needs to be transmitted in at least in intervals of 20 kilometers per hour. And we can imagine that the service might be interested in this ACC state of simply being enabled or disabled. So this gives the service provider the possibility to select PETs, for example, to generalize speed data, to recode the speed data to multiples of 20 kilometers per hour, and to also generalize this ACC state to enabled and disabled, such that all more specific states of this system are recoded or are generalized. So finally, I want to mention a few goals we had for the design of this process and which we discussed in the paper. This was, first of all, reproducibility. And here we would argue that the process is reproducible to a certain extent, where we suggest PETs for certain kinds of data. However, this is limited by the fact that in some cases, the applicability is limited and will be specific to the service that this process is applied to. Also, the third step of the process rather proposes guidelines for service providers to apply. So these are not completely unambiguous. However, we also wanted to create a process that is both applicable as a standalone process, but also complementary to other methods, like the risk-based methods I mentioned in the beginning, which often suggests a list of potentially PETs, which could then be narrowed down with a process as we have proposed it here. And the third point here is that the process really targets data minimization. And I think this is an important point to mention again, because this process does not only target data quantity, asking the question of if a certain datum should be collected or not, but it also asks the question of which precision is required and what's really the required quality for the data. So all in all, we proposed, first of all, a general process for the selection of data-dependent PETs. And then we applied this to the automotive domain, also proposing this taxonomy and general applicability table for the automotive domain. And we would argue that it nicely complements existing approaches in this field and also supports data minimization. In future work, we want to apply this to other domains as well, extend it, maybe investigate the possibility to develop similar processes for other types of PETs and integrate it into general software engineering and requirements engineering approaches. And with that, I conclude the presentation and thank you for listening.
Hello everyone, I'm Sama Khalfawi and I will be presenting today our hybrid secure device pairing protocol called COOB. We will start by a brief introduction of the secure device pairing procedure. In the pairwise context, we have two devices, the enrollee, that is the IoT object, and the introducer, that is an authenticated device belonging to the user. These two devices aim at establishing a secure communication channel between them based on 5 main assumptions. The first one is that the two entities have no pre-shared security knowledge, such as symmetric keys or certificates. Second, the two devices are considered uncorrupted by the adversary. Third, the IoT device is assumed to have limited input-output interfaces, such as an LED, photo sensor, and a button. Fourth, the users are considered non-experts in terms of security regulations, which means we are facing a high human factor error when performing relatively complex human interactions with the devices. And finally, the user is assumed to correctly initiate the pairing process between the intended devices. This means that he cannot mistakenly pair with another potentially malicious IoT object when assuming that he is pairing with the legitimate IoT device. Therefore, in our analysis, we will evaluate two main criteria: the robustness against attacks such as the man in the middle, and the usability aspects in terms of the degree of user intervention and the amount of time required for pairing. In this slide, we will introduce the adopted attacker model on the main communication channel used for the key establishment. The most adopted adversary model is a variant of the Doliviao intruder with 5 main actions. So the adversary can block, overhear, delay, and replay any transmission. He can also generate his own messages and inject them into the channel, which is called forging. And he is assumed to have a perfect knowledge of the protocol execution, which means that we do not consider any security by obscurity techniques. Therefore, based on these powers, the attacker can completely control the exchanges over the in-band channel. Based on this attacker model, and using the band logic analysis, it has been demonstrated in the work of Clycomb and Chen that the key authentication is not feasible based on a single communication channel, which means that an auxiliary source of security is needed to accomplish this objective. In the literature, there are 2 types of secure device pairing schemes. The first variant is the protocols relying on an auxiliary channel called out-of-band to authenticate the keys exchanged over the main insecure channel, also referred to as in-band channel. These particular channels tend to have different communication properties to limit the capabilities of the adversary. As an example, we can use the visible light communication to serve this purpose. In this example, the out-of-band based scheme uses the Diffie-Hellman key exchange protocol. During the key establishment procedure, the adversary will block the previous exchanges and he will inject his own fraudulent keys, which will result in computing a different key on each legitimate device that is reconstructible by the adversary. This is where we can use an auxiliary channel that is partially out of control of the adversary, and we will use it to authenticate the computed key up to a certain probability related to the number of bits of the authentication string. There are 4 main categories of out-of-band channels based on their nature. First, we can find the audio channels using sound to transmit the bits. Also, we can use the visual channel either by applying visible light communication or by taking pictures, for example, of a QR code. Also, we can use the haptic channels that either require an intervention of the user to apply, for example, a pattern of pressing buttons, or by using vibrations to transmit the authentication bits. Also, we can use a radio channel, for example, NFC. However, recently it has been demonstrated a man-in-the-middle attack on the NFC technology in the work of Actor et al. Therefore, we're going to be focusing solely on the audio, visual, and haptic channel for the next analysis. As for the security characteristics of these out-of-band channels, they can be abstracted into three main categories. We can find the confidential out-of-band channel that is supposed to eliminate any capabilities of the adversary. We have the protected out-of-band channel that limits the capabilities of the attacker to overhearing, blocking, and delaying the messages. Also, we can find the authentic out-of-band channel that only allows the attacker to overhear, block, delay, and replay, which means he cannot forge his own messages. Also, these channels tend to require some kind of user intervention. In the work of Fomichev, it has been categorized into four main actions. So either to relay a secret from one device to another, as done in the MANA-1 protocol, either to generate a secret and inject it into the two devices, as applied in the pin entry variant of the widely used secure simple pairing protocol used in Bluetooth. Also, the user can compare two outputs displayed by the two devices, as used in the numerical comparison variant of the secure simple pairing protocol, or to simply set up the devices, which is required by all the out-of-band channels. Either to, for example, we can be the channel can need to set up them by placing them next to each other or by establishing a line of sight. So these channels actually provide security against a Delovia intruder. They are fairly easy to construct. However, for the confidential out-of-band channels, they are quite hard to reach. Also, these out-of-band channels tend to have low data rates, which makes the transfer of long authentication string not feasible, and makes the pairing time quite significant. Also, they tend to require an extensive user involvement, which is prone to human factor error. As for the second variant of secure pairing, we have the context-based schemes that rely on the ambient environment as a shared source of randomness based on the onboard sensors of the devices. As we can see here, the two devices are co-located within an authentication zone that is considered secure, since the adversary is always assumed outside of this area in order to eliminate any possibility of him sensing the same contextual information. These two devices will extract entropy from the ambient environment in order to create a secret information that will be applied to one of these actions, either to generate a key or to encode secret bits based on that secret information, that contextual secret information. Oh, that's right. Or to create a fingerprint that can be used as a proof of co-presence. So as we can see that this technique applies minimal to no human interaction. It is quite fast for radio and magnetometer based ambient environments. However, this technique tends to perform poorly for event-triggered variables in low-activity environments, such as the acoustic environment at night, where there is not a lot of random actions around. For example, the Perceptio protocol takes between 2 and 20 hours to pair two devices. Also, this technique has as a requirement that an attacker is outside of the authentication zone, which is not always simple to accomplish. And the contextual pairing doesn't it doesn't support the idea of performing it in an environment controlled by the adversary. We'll be referring to such environments as hostile. As a summary, the out-of-band based schemes provide security against a closed Delovia intruder, which is not the case for the context-based schemes. However, regarding the usability aspect, the context-based scheme provide a fast device pairing with less user involvement in comparison with the out-of-band channels. This is why we will try to combine the two approaches to provide the needed security in a hostile environment in comparison with the typical contextual schemes. And we aim at providing a faster and more user-friendly device pairing in comparison with the use of only an out-of-band channel. Before diving into presenting the details of our protocol construction, we will briefly present the chosen context-based protocol that will encode some of the authentication bits using the contextual information collected from the radio environment. The protocol proposed in the work of XER uses a variable called the channel state information. We can find it in any OFDM-based technologies such as Wi-Fi. These measurements will be used to construct a matrix called S-box that will be used to encode and decode the secret bits by the legitimate devices. Basically, without having having similar contextual measurements, the attacker will not be able to compute the proper S-box, and consequently, he will not be able to retrieve the secret. This protocol achieves a high success rate in exchanging a 256-bit key in just 2 seconds, which makes it suitable for our construction. As we stated previously, in our protocol, we will be using the dancing signals scheme for our contextual model and a visual out-of-band channel employing the visible light communication technology. The protocol will start by generating on each device 2 random variables that represent the Diffie-Hellman private key and random nonce that has a bit length equal to L. The protocol has in total 6 exchanges, 4 of them on the main insecure channel represented in black, and 2 of them and 2 out-of-band exchanges represented in blue and red. In the first exchange, Alice will send her modified Diffie-Hellman public key G to the power of A minus RA that can be reconstructed when knowing the true value of the nonce RA. She also sends a keyed hash of the true value of the public key and the nonce. In the second exchange, Bob sends his modified public key and the code word VB, which is the contextual encoding of his nonce RB. In step 3, Alice will use her S-box to retrieve the true value of the nonce RB and will send the XOR of the 2 nonces and an L-bit truncation of Bob's public key G to the power of B. In step 4, Bob will retrieve Alice's nonce value from the message tree and will compute the keyed hash of the 2 public keys using the Diffie-Hellman secret key G to the power of AB. In step 5, Alice will verify the keyed hash received previously in message 4, and if successful, she will send the hashing key to Bob to let him verify the keyed hash sent in message 1. If the verification is successful, Bob will notify the user to confirm the pairing on Alice by pushing a button. So we have evaluated the security of our protocol in the symbolic model against 2 intruder models. The ordinary contextual adversary that is located outside of the authentication zone, which prevents him from collecting the correct contextual information represented by RC. The second type is the sophisticated contextual adversary that can get hold of the contextual information either by violating the authentication zone requirement or by controlling the ambient environment, also called a hostile environment. First, we have tested the secrecy of the authentication values RA, RB, and the contextual information RC. This property holds only for an ordinary adversary, which validates the powers of the sophisticated adversary. Then we have tested the secrecy of the established key at the end of the protocol run, and it holds for both attacker models. Finally, we have evaluated the key authentication by testing the injective agreement property that guarantees that the two devices agree on the established secret key in a single session. Therefore, our protocol guarantees the secrecy and the authentication of the key establishment process, even when the adversary is able to violate the authentication zone requirement, which is not feasible by any traditional context-based schemes. A final note, without using the nonce exponentiation to temporarily hide the true values of the Diffie-Hellman public key, the combination of the two pairing techniques will be trivial, and the protocol will be vulnerable against the sophisticated contextual attacker. As for the pairing time estimation, we have conducted a comparison between the use of our hybrid proposal against the use of only an out-of-band channel to transfer all the security bits. Since the implementation of our contextual model is still in progress, we have used the published results in the work of XEER to estimate the average time percentage gain of our scheme against the same protocol structure when relying only on the out-of-band channel. This has been done mainly to assess the advantage of this hybrid proposal without dealing with any differences in the protocol structure or the cryptography in use when comparing against other out-of-band based pairing protocols. To conduct this analysis, we used the bit generation rate metric that is equal to 140 bits per second. That stands for the number of secret bits agreed upon after the execution of the contextual protocol. In the first graph, we will find that the pairing time grows faster based on the number of transferred bits when using only the out-of-band channel. However, it requires less pairing time using COOB. This gain can be seen in the second graph, where the contextual model in the hybrid scheme provides a time percentage gain that grows up to 39% for a nonce bit length equal to 80 bits. This gain enhances the usability aspect when dealing with a secure low bandwidth out-of-band channel. As a conclusion, COOB combines the use of an out-of-band channel and a contextual encoding scheme. Our proposal enhances the security against a sophisticated contextual adversary that is not supported by any other contextual protocol. COOB has been symbolically validated by the Tamaram prover, and it has been tested to validate both the secrecy and the authentication of the key establishment process. Our protocol provides a usability enhancement by reducing the pairing completion time when using a low bandwidth out-of-band channel up to 39%. As for the future work, we aim at implementing the chosen contextual model to validate our time approximation. Also, we want to conduct a power efficiency evaluation to validate the ease of adoption of our scheme by the constrained IoT devices. And finally, we aim at extending the chosen contextual scheme to use the magnetometer readings as an alternative source of randomness when we don't have a Wi-Fi access point visible to the two devices. Thank you.
Hello everyone, my name is Isan. I'm the fourth year PhD candidate from the University of North Carolina at Charlotte. Today I'm going to present our paper about classifying security vulnerabilities into cyber weaknesses through a novel neural network design and represent the importance of this classification for proactive cyber defense. Every day, million lines of codes are written to develop thousands of applications and softwares. These programming efforts are not perfect, and any mistake at any level of production can make the system vulnerable to cyber threats. In the context of cybersecurity, vulnerability is an instance of software weakness, defined as an unintended flaw, mistake, or bug in a software or an operating system. These vulnerabilities are the result of faulty design, programming and implementation error, and improper computer or security configuration. Some of these bugs get fixed by patches released by vendors, but those left unpatched may create security holes where cyber criminals can exploit and perform malicious activities and compromise the system accordingly. Software weaknesses are often discussed and defined in the context of the Common Weaknesses Enumeration, or CWEs. These CWEs are a community-developed list of common software security weaknesses maintained by MITRE. CWE is a hierarchically designed dictionary of software weaknesses for the purpose of understanding software flaws, their potential impacts, and identifying means to detect, fix, and prevent those shortcomings. On the other hand, Common Vulnerabilities and Exposures, or CVEs, are a list of publicly disclosed security vulnerability reports, where every report is assigned by a unique ID. CVEs are brief and low-level descriptions representing the standard means for sharing cybersecurity vulnerabilities within a specific product. Basically, CWE is a dictionary of software vulnerabilities addressing the underlying flaws, while CVE is a set of known instances of a vulnerability exploited in a particular system. CWEs shares a number of important factors such as description, common consequences, potential mitigations or detection, and related attack patterns. While CVE is a vendor-specific low-level description, CWEs explains how a CVE can be exploited, representing the conditions and procedures, why a CVE is exploited by describing the cause, and what are the consequences of the exploitation as impacts. When the vulnerability patching is infeasible, the classification of CVE into CWE becomes extremely important because CWEs can provide the means to understand the CVE implications, find weakness level mitigation, and helps to characterize vulnerabilities to develop further fine-grained course of action defense. Let's take a look at one example. Given this CVE stating a SQL injection vulnerability in the LaaCan PGSQL library v4052 allows attackers to execute arbitrary SQL statement. We see it mentions execute arbitrary SQL statement as attack action, the library as a vendor-specific cyber object, and the SQL injection as the consequence of exploitation. However, this is not enough, and there is a need to extract higher level information to specify the characteristic of the security threat and accordingly find potential mitigation techniques. To this end, let's take a look at these CVEs associated CWE89 that provides beyond the product level of knowledge about this SQL injection vulnerability. It states faulty neutralization of a special element as the cause of attack, modifying intended SQL command to answer how it is exploited, and mentions read and modify application data and bypass protection mechanism as the consequence. Obtaining these factors is closely associated with the paradigm of pinpointing applicable defense actions. In the meantime, CWE89 recommends several detection methods such as using database or web application scanners, or prevention methods such as environment hardening or output encoding. As I mentioned before, CWEs as non-disjoint classes are organized in a hierarchical structure as a tree to reflect the inheritance relationship in which every non-root CWE inherits the whole characteristic of its parents. This hierarchy is very important when the most fine-grained CWE is not available for one CVE. where we can leverage the characteristic of the lowest level available node and its potential parents to estimate the characteristic of a vulnerability roughly. For example, if the fine-grained SQL injection CWE for this CVE is not available or is not classified, we can leverage the closest available coarse-grained CWE in the path to approximate the characteristics, like injection. Our discussion shows the value of classifying CVEs to their corresponding CWEs. Thanks to the cybersecurity experts and engineers, a great manual effort has been made initially by both MITRE and NVD to classify some CVEs to one or more CWE classes. Considering the growing number of CVEs and the high labor cost of manual classification, MITRE successfully classified about 5% of the CVEs and then stopped the process. NVD increased the quantity of CVE classification by mapping about 85,000. Although MITRE classified a smaller number of CVEs compared with NVD, it covers a higher number of unique CWEs and performs hierarchical and more fine-grained classification. On the other hand, NVD classified more CVEs, but it took less number of CWEs into the account without addressing the hierarchy. Due to a different point of view and approach, MITRE and NVD classification conflicts most of the times, and it's not possible to neither compare nor combine their classification. In the meantime, there have been several good research efforts other than MITRE and NVD to analyze CVEs to enhance the searching process and to perform CVE categorization automatically. However, these approaches are limited, incomplete, and without considering the hierarchy. Therefore, to the best of our knowledge, no solution has been proposed for automated mapping from CVEs to CWEs yet, and we are the first to propose such a model. Finding an automatic way for CVE categorization is extremely important since traditional manual techniques are costly, ineffective, problematic, and not practical. Our objective is to build a tool that takes the CVE descriptions and provide the corresponding CWE ID. Creating such an automatic system is challenging. First, CWEs are organized in a hierarchical structure. CVEs can be categorized with multiple labels. In this case, each CVE instance can be classified into one or more interdependent CWEs that belongs to the same path. In addition, some CWE nodes in the hierarchy class can be accessed from more than one path in the CWE tree structure. Third, there is a semantic gap in and between the language of CVEs and CWEs that makes the feature extraction phase challenging. So performing an efficient semantic analysis is necessary in order to identify the connection between similar concepts used in the CVE and CWE context. Last but not least, a considerably small percentage but high quality classification CVEs are provided by MITRE. On the other hand, NVD delivers a higher percentage of CVE classifications, but it used a lower portion of CWEs. So there should be a trade-off to process small and imbalanced datasets and classify CVEs into the most fine-grained CWEs, along with exploring the entire nodes in the path. As you can see here, our work to build an automatic system to classify CVEs to CWEs has 4 key contributions. 1. The development of first algorithm that automatically classifies CVEs to CWE classes. 2. A novel design of hierarchical neural network that is able to trace CWE classes to the most fine-grained in the CWE hierarchical structure. 3. A new approach to extract semantic and statistical features from CVE descriptions and compute the score that reflects the importance of the features in describing the vulnerabilities at each level in the CWE hierarchical structure. And 4. An adaptive learning technique that incorporates the computed feature scores by TF-IDF in a neural network framework to allow an automatic adjustment for feature scores to reduce the classification errors. Our proposed algorithm consists of 3 steps, including pre-processing, feature extraction, and hierarchical neural network decision-making process. The preprocessing component extracts the text from the description of input CVE instance and cleans it to generate a normalized version of it. First, it converts every word to lowercase, and then it removes so-called stop words to reduce the noise and feature space dimension. In the next step, it removes punctuations and special characters that do not convey important information. Then, it performs stemming to reduce each word to its root in order to identify the relationship and commonalities across large text documents. Synonym word coding is the last step of preprocessing. It groups the synonym words in the context, assigns a code word to represent each group, and replaces all the synonym words with the code word which represent that group of synonym words in the context. These words are manually extracted from the alternative word section in CWEs and the CWE glossary which is provided by MITRE. This synonym vector coding helps in reducing the variance within documents in the same category and in increasing the distance between different categories. In the feature extraction component, the normalized text is processed to extract features to characterize the statistical and semantic properties. To this end, the input text is analyzed to generate a list of unique unigrams, bigrams, and trigram terms. The window size n in n-gram analysis is a hyperparameter and set experimentally. We tend to set this value to 1, 2, and 3 to satisfy stability and to avoid overfitting, since longer n-grams dramatically increase the number of word combinations that are rarely found in CVE instances and may cause overfitting in the training process. According to power law distribution, we remove the n-grams with the frequency less than 3 from the feature space. The remaining unique n-grams get a unique index to generate the dictionary as feature space. In order to generate the feature vectors for each entry, we create a vector of size d-1, which equals to the size of dictionary. The initial value of each element in this vector is 0. Then, we extract the n-grams from each CVE descriptions, and then we look for their index in the dictionary. If the n-gram exists in the dictionary, we assign 1 to the corresponding vector item. Hierarchical decision making is the third step in the CVE classification algorithm. This step takes the feature vectors computed through the previous component and estimates the CWE classes associated with the CVE instance of interest. It follows a top-down approach by training a classifier per node in the CWE tree. For each node, a decision is made using the classifier that either leads down to a different classification node or to the leaf. This hierarchical architecture allows each classifier to focus on learning two aspects of its children: the details that distinguish between the classes of its children, and learning the common features between the classes forming each child. This approach helps to simplify the design of this classifier to reduce the computational cost, as well as improving the accuracy of the system by making each classifier to focus on its children without getting confused with the other nodes. In the classification procedure, for each node, the neural network takes the feature vector and predicts the label of the class in the next level of the tree. In this case, the neural network starts to classify CVEs to CWEs that exist at level 1. In the next level, the neural network finds the predicted CWE classes in the previous level and takes their children for the next level of classification. Each neural network consists of one hidden layer. The number of neurons in the hidden layer equals to the number of classes present at the level L in the CWE tree. Each neuron is fully connected to the input feature vector. The sigmoid function in every output neuron generates a probability score. If this value is higher than an imposed threshold, it means the input feature vector belongs to the class associated with that neuron with the high probability score. Instead of randomly initializing the weights, we set the TF-IDF score of each engram in feature space with each class. This score shows the importance of that engram feature for each class at each level. So if a feature is a key signature of one class, the connection weight will be high, which will help the neural network to predict the correct class. This simple neural network has been employed for three main reasons. First, to reduce the computational cost by reducing the number of variables that a neural network needs to learn. Second, to avoid the overfitting problem, especially when the size of the training dataset is small. And third, to allow mimicking expert thinking process when classifying CVEs to CWEs according to the terms mentioned in the description and their knowledge about the CWE classes. A comparative evaluation experiment have been conducted to evaluate the performance of ThreatZoom on the labeled CVE sets provided by MITRE and NVD. The evaluation compares the estimated CWE candidate list generated for each vulnerability in two different levels, including coarse grain and fine grain. To be more precise, if the model predicts one or a sequence of CWE classes which are not necessarily full path toward the leaf, it is considered as coarse grain classification. On the other hand, fine grain classification happens when it successfully predicts the full path to the leaf, where here the leaf means the labels in the ground truth. Our model successfully results 92% and 94% accuracy in fine grain coarse grain classification over NVD set. In addition, it shows 75% and 90% classification accuracy in MITRE dataset. Although there is a 17% gap in accuracy of classification between NVD and MITRE, ThreatZoom shows it is able to learn short corpus and imbalanced data with the promising performance, and it can perform even better if it receives more training examples from the MITRE. In the second experiment, the hierarchical neural network framework is replaced by a regular flat one, such that the neural network considers all the class in one-shot classification process, regardless of their hierarchy, and initialize the weights randomly during the training process. In the third experiment, the single-layer neural network classifier is replaced by two-layer, and the neural network weights initialized randomly during the training process. The results show a significant difference in the performance of ThreatZoom and the other models. We also took one more step forward and tried to predict more fine-grained CWEs. Reported results show not only ThreatZoom perform as good as the MITRE and NVD engineers who are well trained for these tasks, but also it accumulates their experience to offer even more fine-grained CWEs. ThreatZoom obtains more fine-grained classification for about 47% and 95% of those CVEs that were correctly matched by MITRE and NVD respectively. To validate these results, we used our domain expertise to manually inspect 100 randomly selected CVEs that received fine-grained classification by our tool. This paper presents an automated technique for fine-grained classification of CVE instances to CWE classes. To this end, we discussed the existing challenges and shortcomings and introduced ThreatZoom as a novel blend of text mining techniques and neural networks to map security vulnerabilities to weaknesses. To the best of our knowledge, ThreatZoom is the first automated system that addresses existing challenges and limitations of classifying CVEs to CWEs. This tool is already being developed to leverage word embedding and deep neural network to better classify CVEs to CWEs following the MITRE standards, extract threat actions out of CTI reports, automatically calculate threat severity scores, and find the potential course of action mitigation and detections accordingly. Thank you, and I hope you enjoyed this presentation. Please let me know if you have any question.
Hi everyone, my name is Liangjia Li. I come from Guangxi Normal University in China. Today, I will introduce to you the works of our team. The title of my presentation is A Robust Watermarking Scheme with High Security and Low Computational Complexity. The content of my report includes the following parts. The first part, I will briefly introduce the basic idea of watermarking technology. The second part, I will introduce the DST watermarking scheme. And the third part, I will introduce the work of our team. And then, I will present the experimental results. And finally, I will summarize our work. Firstly, I introduce what is watermarking idea. The base idea of watermarking technology is to embed digital watermark into digital contents by using related watermark embedding algorithm. The digital contents including images, videos, or audios. Then the embedded watermark can be extracted via utilizing extraction algorithm. Sometimes the watermark image will be attacked by cropping, rotation, no attention, and so on. Watermark algorithm mainly includes 5 basic characteristics, and they are impossibilities, robustness, capabilities, securities, computational complexity. There are often contradictions between these characteristics. For example, the better impossibilities and the worse loudness. Moreover, the impossibilities is measured by PSNR and SSIM. Generally, when PSNR larger than or equal to 37 dB or SSIM greater or equal to 0.93, and the impossibility is accessible, and the loudness is measured by NC or PER. Generally, NC is greater than or equal to 0.8 or PER less than or equal to 0.2. The loudness is accessible. Watermarking can be divided to embedding ways, and they are spatial domain injection and the transfer domain injection. The spatial domain injection refers then the pixel values of cover image are changed directly to embed the watermark. It has smaller computational complexity and large capacity, but poor loudness. And the transform domain injection refers then the transfer coefficients of the cover images are used to embed the watermark. It has greater loudness, but its computational complexity is higher. Recently designed a watermark algorithm that can satisfy the advantages of two watermark embedding methods is a research hotspot. For example, the watermarking information is embedded into the DC coefficient of this T, and the process is complete directly in the spatial domain. This embedding method can meet advantage of about two embedding methods at the same time. The figure shows how odd values change in spatial domains after the DC coefficient is modified. As shown in the figure, the match A performs DCT and the value in the upper left corner is DC coefficient, and the rest are the AC coefficients if the DC coefficient changes. For example, adding 16 and then perform in Y DCT, and the result is as the max D. We can see then the max D can be obtained by adding fixed values to max A, and the specific additions depends on the size of max A, and the relation is as this equation. The process of embedding methods by modified DC coefficients is as follows. Firstly, the host image is divided into A type A blocks, and then the DC coefficients of this T is directly calculated in the spatial domains, and then the binary watermark is inscribable, and then all blocks of the host image are embedded with the watermark information. Using this embedding method, 512 times 512 watermark images can contain 64 times 64 watermark information. We can find then this embedding will access several obvious problems. Firstly, all A type A blocks must be embedded with watermark. Therefore, the watermark is embedded into the host images. All pixel value of the host image will be changed, which will lead to poor impossibility. And from the experiment results, The low bandwidth is not ideal under some attacks, and security is not very high because another challenge for is Hierarchical. In order to resolve the above problems, we propose a new watermarking scheme. Firstly, the initial parameters x1 and the controls parameters u of the TLCM are taken as the secret keys, and the strings which the required lengths are generated by iterating the TLCM. And then these values are mapped to the relative decimal values by the proposed mapping method. Then these decimal numbers are mapped into the corresponding binary numbers. Finally, these binary numbers are transformed into two-dimensional matrices with the same size as the watermark. Then the equality watermark is obtained by performing XOR operations between the watermarks and matrices. Before embedding the cover image, firstly, the host image is divided into 4 times 4 blocks, which are not overlapping, and the blocks with the same number as the watermarks are randomly selected, and their positions are recorded. Then the DC coefficient of the select blocks are calculated directly in the spatial domains. Finally, the proposed scheme can greatly Finally, the equivalent watermark is embedded into the blocks with the new proposed watermarks embedding algorithm. Obviously, the proposed schemes can greatly improve the security of the algorithm, and it is worth noting then, since the host image is divided into 4 times 4 non-overlapping blocks, only a part of blocks are used to embed the watermark. Specifically, only 1/4 of blocks are used to embed the watermark, and only 1/4 of the pixel values are changed in the host image, which will improve the impossibilities of the watermark image. Using the proposed watermarking embedding method, the proposed watermark, the robustness of the exact watermark is also improved compared with other research. The detailed watermark embedding procedure is as follows. According to the equality watermark WE, if WE equal to 1, DC coefficient of the select blocks is modified by this equation. If WE equal to 0, the DC coefficient of select block is modified by this equation. And then select the optimal modifies the according to this equation. Finally, the block which embedding with the watermark information is updated according to this equation. The process of watermarking instruction is the inverse embedding. Firstly, the watermark image is divided into 4 times 4 blocks, and then the positions then contain watermark information is determined. Then the encrypted watermark is extracted according to the extraction algorithm. Then the encrypted watermark is decrypted to obtain the final watermark. Now I introduce the experiment result. We select a 512 times 512 gray image and a 64 times 64 binary watermark for experimental simulation. The simulations results sustain the PSNR and SSIM values of all watermark images are greater than 42 dB and 0.8.9a, which are greater than the exposed values, which means then the proposed skin is very impossibilities. Moreover, for all watermark images, the watermark can be extracted completely. In order to further illustrate the impossibility of our skin, we compare 3 states of the works. These 3 works are also based on this T transform. For the compared result, the PSNR value of 3 watermark images obtained by our work are higher than other works, especially so compared with work 3. In the works, the 512 times 512 gray cover image can only contain a 32 times 32 binary watermark, while the 6 gray cover image can embed this with a 64 times 64 binary watermarks in our work. The watermark capacity of our work is 4 times 10 of 3, and the PSNR of this work is still higher than their work. Therefore, it's proof again that the proposed method has excellence in possibility. Next is Lobanese test. The purpose to test whether the extracted watermark can be recognized when the watermark images is attacked intentionally or unintentionally. In this words, we use different attacks to test, including noise attack, filtering attacks, cropping attacks, and so on. The above figure shows the linear watermark image after being attacked, and the below figures are the extracted watermarks. From the visual point of view, the extracted watermarks can be recognized. Moreover, the ANC and PEDR values are within the exposed range. For other test images, similar results are also obtained, and the results are shown in Figure A and Figure B. We can see that the ANC values are basically greater than 0.85 and PEDR are basically less than 15%, which means that there is no obvious perceptual distortion between the extracting watermarks and the orange one. Besides, we further aggregated the Lobanese by using Gaussian low-pass filter attacks and JPEG compression attacks with dynamic parameters. The parameter sigma of Gaussian low-pass filter is set from 0.5 to 4.5 with a step of 0.5. And the parameter's quality factor JPEG compression is set from 19 to 13 with a step -10. The figure C, D, E, and F shows the result. We can see that the PEDR values are basically less than 15%, and the PEDR and the ANC are greater than 0.85. In addition, we compared Lobanese with 2 related works to prove the greater Lobanese of our work. Figure A and B present PEDR comparison results. We can see that the PEDR values of these works are both lower than compared works under value attacks. In other words, the distortion degrees of our work under different attacks is lower than of other works. Next, we analyze the learning types of algorithms compared with the implementations of DST. The advantage learning types of algorithm is faster than of reality. Whether in watermarking, embedding, or watermark extraction, the total learning time is about 5 times faster. Finally, I summarize our work. The cover image is divided into 4 types for non-overlapping sub-blocks, and some blocks are used to embed watermark, which can improve the impossibility. To achieve high security, the watermark is encrypted by a binary matrix obtained via LCM before it is embedded into the cover image. The proposed watermark embedding procedure can further improve the robustness. The DC coefficients of the selected blocks are calculated in pixel domain to shorten the execution time. My presentation is over. Thanks for your attention. Any questions welcome.
Hello, this is Chuning Han. Today my presentation topic is private global generator aggregation from different types of local models. The outlines of this presentation includes background, motivation, preliminary, our scheme, security proof, and evaluation. Let's start with background. As we know, as machine learning facilitates more and more sensitive areas, data privacy becomes a major concern. To address this problem, generative adversary network is a thriving research topic which can be used to generate fake or synthetic data to replace real sensitive data to be released for outside research. However, this method have two major problems. Firstly, generated data could encode or reflect sensitive information of training data. Secondly, sometimes data is distributed among multiple parties. Therefore, in this paper, we are aiming at aggregating a global generator from different types of local discriminators. Our generator aggregation method will have many applications, We take COVID-19 as an example to illustrate. A world-level organization wishes to use data from some countries to help other countries, lack of data and research resources. Let's say China, Japan, and South Korea are willing to contribute. However, they are not willing to disclose their sensitive data to the World Health Organization because of the concern of patients' privacy. The World Health Organization will aggregate a global generator from the 3 countries to achieve a global generator and use this generator to generate synthetic data and use those synthetic data to help other countries. Let's say our motivations. Firstly, let's say why traditional parameter-based aggregation methods fail. Because they usually assume local parties and the global party develop exactly the same type of models and structure. Secondly, averaging local models parameters might not directly result in an accurate global model, let alone those methods use differential privacy to protect sensitive information of training dataset. Thirdly, local party might use different types of models in which all different types and structures of parameters cannot be averaged. Let's say why our global generator will be appealing. You may ask, why not use anonymous data? By removing identifiers such as names, addresses, incomes, those data can be protected. Actually, this method is kind of risky because the remaining data combined with some auxiliary dataset can help re-identify the person. So you may also ask, why not let those local models to generate their own data and send to the World Organization? That is because the total number of generated synthetic data is unknown at this moment. Also, local models may use different types, and the quality of generated samples from those local parties may of different qualities. Therefore, our goals are to achieve global generators for local parties, even they have different type of local discriminators, and also we provide privacy protection for local parties' sensitive training dataset. Let's say preliminary. We only use one preliminary in our work, that is GNN. We show the training process of a GNN used in our method. It includes 5 steps. The first step is discriminator is trained on a bunch of real data and a bunch of fake data. Real data comes from training datasets and fake data comes from the generator. Second step is set the discriminator untrainable. That means its parameters will not be updated. Thirdly, the generator and the discriminator are combined as a GNN. Generator generates a new bunch of fake data and feeds it to the discriminator. The fourth step is the discriminator computes loss on that bunch of fake data and computes gradients. Finally, the generator updates its parameters using the gradient. Let's see our scheme. Firstly, we show the overview of our scheme. Local parties possess sensitive datasets. The global party wants to achieve a global generator to generate synthetic data. Local parties will train different types of discriminators, and the global generator will generate fake data to train those discriminators. After training those discriminators, the global generator will generate a new bunch of fake data, feeds them to the discriminator, and the discriminators will predict on this bunch of fake data and output noise loss. By using noise loss, sensitive training datasets can be protected. And the discriminator will select one discriminator as a representative, collect other discriminators' noise loss, use the average to compute gradients for the global generator. Let's go through the algorithms. Firstly, the generator will generate a bunch of fake data. The discriminators will be trained on this bunch of fake data and a bunch of real data from its own sensitive training datasets. Then set discriminators untrainable. Then the global generator will generate a new bunch of fake data, feed them to the discriminators. Discriminator will compute loss on this bunch of fake data and add Gaussian noise to the loss. The discriminators will select one discriminator as a representative to collect other discriminators' noise loss and average the noise loss, and then use the noised average loss to compute gradients for the generator. Then the generator will update its parameters using these gradients. Notice that in our algorithm, we use an adaptive noise level. That means we set sigma in the Gaussian noise as the half value of first bench discriminator loss. Let's say security proof. We use a very simple structure of a GNN to show how discriminator's noise loss will affect generator's gradient. We take W21 as an example parameter of generator as an example to say how noised discriminator loss will affect the gradient for generator's parameter W21. As we can see, we take the green line as an example to show the chain rule. The chain rule will be like this equation. From this equation, as we can see, because E is noised, so as gradient for A prime 31, so as for Z prime 31, so as for W21. Therefore, gradient for W21 is noised. Let's say the first layer, W11, this parameter's gradient will be a little bit different because W11 equals because Z11 equals W11 times X multiplied X, in which X are input samples. The gradient for W11 will have X as coefficients. However, notice that those input samples X are generated fake samples from the global generator, not real samples from local party sensitive training data. Therefore, the gradient for W11 is also noised. As we can see from those analyses, we can say gradient for the generator will be noised. Therefore, the generator cannot steal sensitive information from local parties' sensitive training dataset. Okay, let's say evaluation. In this picture, we show some real samples and fake samples generated from the global generators. AD are real samples from MNIST and Fashion MST. BE are generated samples from a global generator generated only one party. CF are generated samples from the global generator aggregated from 5 local parties. As we can see, generated samples look alike as real samples. And there are more local parties, the generated samples will look more blurry than the real samples. To compare local parties' accuracy to the global parties' accuracy, we firstly list the average local parties performance on this table. For MNIST, local parties achieve average 97% of accuracy. For fashion MNIST, local parties achieve about 88% of accuracy. Let's see for different local party numbers, the global party's accuracies compared with local party's accuracy and the baseline. As we can see, our method for the global generator achieve slightly higher accuracies than local parties. That means our aggregation method can achieve higher accuracies than a single local party. However, compared with baseline, our global generator will not achieve higher accuracy. That is because generated data will not be as precise as real samples, and also we add Gaussian noise to discriminator loss to protect privacy. Those reasons cause some decline of the accuracy. Let's say compared with related works. There are three major types of related works. The first one is they use intermediate feedbacks from discriminators for the generator to update. However, those methods did not provide privacy protection. The second step of related works, they use differentially private gradient descent to achieve differentially private GNNs. However, those methods are really inefficient. They use TensorFlow Privacy Library to train GNN to implement. This library can take hours to train GNN even on TPU. The third type is those methods use differential privacy on majority voting labeling plus a simple classifier to achieve a differentially private GNN. Those methods are also inefficient. Additionally, all this related work, they assume local parties develop the same type of discriminator. We compare our scheme to three related works. Due to lack of experiment results on fashion MNIST, we only compare accuracies achieved on MNIST. From this table, as we can see, our method achieved the highest accuracy compared with those three related works. It means our scheme will outperform those related works. In conclusion, the contributions of our work are three main aspects. We achieve two main goals: global generators for local parties, suitable for different types of local discriminators, and provide privacy protection for local party sensitive training data. Secondly, we separate GNN into two parts: discriminators in local parties and a global generator in the global party. We choose discriminator loss as vehicle to aggregate the global generators. We add noise to discriminator loss computed on generated samples. By adding noise to discriminator loss, we can prevent private information leakage from discriminators. Then the references. Thank you for listening.